Well, let's see. This is a free-form thing, so this is going to be very interesting because I have nothing prepared. Well, except that I thought of something that I might tell you if you guys are too shy. So let me introduce myself for the people who don't know what I'm doing, and then also go a little bit meta first because I know your neighbor, and you might be interested in how that came about. So, my name is Clemens. I work in the Windows Azure Service Bus team as a technical lead. I'm a program manager. My boss's boss is Scott Guthrie, if that name rings a bell at all, in the PM organization in Windows Azure. And I am kind of doing the technical strategy for the Service Bus workload for the Service Bus server, service and the server. And I've been on the Service Bus team for a very long time now, almost too many years to count, 5 years. So I started when the team had like 4 people, and we took the service from a little incubation, which was running literally under someone's desk, through a number of labs and being handed like a hot potato from manager to manager because they didn't know what to do with this thing, to one of the Windows Azure services as you see it today, and it's a service you can go and commercially use. I've been working in the Redmond team for 6 years, or in Redmond for 6 years. I started with the Windows Communication Foundation as a community manager. I think that was the first job that I did, and then also I could work on some features. There's a dispatch model that is behind the first .cf web model, like the REST API that .cf had. I had a little bit of a hand in that. And some other things I wrote before that life. I wrote some software that I made available to the rest of the world that's still around. The blogging engine is still around. It's actually on the first, that's the fun thing. On Windows Azure websites, it is on the first page, which makes me enormously happy. And I need to thank all the contributors and the maintainers who are keeping that thing alive. It's astonishing that that happens. That's a great thing. So I'm a big fan of open source. Nevertheless, I make a lot of closed source, and that's not a problem for me at all. What I'm going to do today, I think, sorry. Why am I here? Now it's an hour and 45-minute drive in favorable traffic, which I had. I saw a lot of traffic jams as I was coming, but they were luckily on the other side. I live now in Viersen in Germany, just across the border. It was a 10-minute drive towards Roermond in Holland, and then coming down 873, and then swinging around to come here. So I live in Germany now, and I still work on the Redmond team, so I have a very long commute. So that isn't too terrible. The team lets me off the hook a little, and I only have to do that commute once every 6 weeks. And then I'm going to stay 2 weeks in Redmond. But I'm working on the Redmond team. I'm based in Germany. I work out of the home office. And so one of the things that I'm doing, and this is why I left my computer on, and I'm going to turn this off, and we can see how we're going to turn off this thing, is I have started a new blog. And so you might take a note of that. On Channel 9, channel9.mcn.com, there is a blog section that you can also find if you have a problem finding this quickly. There's a blog section you can get to. And once you browse through that, you will also find the subscribed blog. And what the subscribed blog is effectively what I'm doing today. It's focused on particular topics. So I have a Hello World section. I talk about environment and scale units. You will hear about that topic today as well. And then I have a tutorial going, interrelated with this, about getting started with Service Bus, the product that I'm working on. And there's 3-4 more episodes coming in that section, kind of laying the groundwork. And then as we go into next year, I'll be going more broadly on the topics, not necessarily getting started, but if you want to know about how sessions work in depth, if you want to hear about stuff that customers have done, I'm going to do some link interviews with customers. So that's going to be kind of a middleware-focused blog that talks about the things that we have in Microsoft, in the middleware platform for Windows Azure and Windows Server. There's folks who own, believe it or not, DTC. There's folks who own, believe it or not, MSMQ. Turns out they're one is in our sister team, one is on my team. MSMQ is on my team. So we'll talk about the futures of those things and how they line up with the things that we're doing. So there's a lot of things to be said about that over the course of the next year. And of course we have new services, new things in middleware. And well, no offense, friends, but about ASP.NET and all the web stuff, they get a lot of airtime, and the middleware things don't get quite as much of airtime. They're for the more sophisticated applications that sometimes are a little more complicated. And so this is the blog for the slightly more complicated things. So that's how you should think about that. So probably also the viewership is going to be a little more exclusive. So I don't expect to get millions of views, but a few 10,000 would be very nice. So much for Meta. So let's talk about what I have on the board here first. This is a certainly crude attempt at drawing a polar bear. I couldn't quite tell how the ears hang on the polar bear, so I left them off. But I don't think actually you can see. Can you see a polar bear's ears? I don't think so, right? Okay, so then it's probably biologically accurate. And that polar bear sits on an iceberg that floats. And as you'll know, an iceberg floating means that there's a lot of stuff underwater which kind of keeps it floating, so we can't quite see that. What I want to talk about today, and we can get to questions, but I want to kind of just get you started, is talking a little bit about the experiences of building a large service and what that all entails, because we don't talk about that a lot. I will not teach you all the details for how you do that. Not that I want to withhold that, but time doesn't allow it to go into all the details. But let me just point out all the things that we need to do, that we needed to do as we did this. So what we started with in let's say until about February 2009. When we were still an incubation team at times, and the thing was called .NET Services after being renamed from BizTalk Services. We thought the world was very easy and happy, and we had a wonderful iceberg. And we were sitting on, we were playing on, we were in the sun. It was all good. It was cold enough so it wouldn't be melting. It's all great. We were happy polar bears. And then slowly we discovered to ship that, to make that commercially available, right? It's February. To make that commercially available by the end of the year, there's a lot of stuff we would do. What we found is that there's about 20% of that iceberg is above water, probably 15%, and that's the features. And the rest that you can't see initially, that you don't think about initially, that's all below the water. So it turns out if you take any of our services that we have in Windows Azure and kind of open up the hatches and look down, there's a lot of stuff that you just don't see. And if you want to build a successful commercial web service or a successful commercial large scalable site, you have to think about a lot of things that you probably haven't thought of before. So I want to talk about that experience a bit because that might be interesting. So let me give you some, probably not numbers directly, but some general idea. We're Service Bus, so I'll talk specifically about Service Bus because that's my team, that's what I work on. I'm not going to talk about storage, I'm not going to talk about compute, but all those services are very similar in at least the challenge, and some of them are actually very similar in structure because they've been adopting kind of the infrastructure that has been built specifically for Service Bus and ACS, and so cache runs on that, and workflow runs on some of that same infrastructure that we had to build. So some general idea. We run in 8 data centers. 8 data centers around the world. So we run in North America and 4 data centers. One is in the west, one is in the east, one is in the north, one is in the south. The 2 data centers in the west and in the east are new. Just came online, I think, last year. Or actually, beginning of this year. Time compresses so quickly. And we have 2 data centers in Europe. One is effectively down the road in Amsterdam. The other one is, or close to Amsterdam, we say Amsterdam. And the other one is over in Ireland. And then we have 2 data centers in Asia. Actually, the data center footprint that Windows Azure uses is larger because we have several places where we also run CDN. The CDN that we run, the content distribution network that we run, has a humongous global footprint, and it does so, and that should be no surprise, because if you're selling Windows and you have 1 billion copies of Windows out there that need patches, getting those patches to that billion of Windows machines is kind of a big trick. So we were forced to run one of the largest networks in the world and one of the largest content distribution networks in the world because of patching, right? Because Windows Update, Microsoft Update, actually needs all that capacity. So one of the things you get to use in Windows Azure is you get to use some of that capacity, some of that infrastructure that was built for that. Windows Azure is built in a certain way underneath the platform infrastructure. That's something that we evolve over generations. We're actually snapping into what our friends at Windows Foundation Services built. If you are interested in getting some insight, you can go to a public site. If I go globalfoundationservices.com, that's our guys who run the data centers, Microsoft Global Foundation Services, and they have some interesting stuff on here, including they have a pretty cool video, if you haven't seen that yet. It's a, I think, 15 to 20 minute video, high quality, about our data centers, several generations of data centers that we run. And so the newest generation, generation 4 of the data centers, they have that in that video too. That is now we've created that in Quincy in Washington, is effectively just a completely air-cooled environment. There's no more water cooling. They're very lofty, kind of very large buildings with what we call IT packs. And IT packs is completely standardized power, completely standardized kind of utilities that are being kind of pre-assembled. We get them from vendors, and then we move them into the facility, connect them, and we operate them on extremely energy efficient as far as power for cooling, etc., is concerned in general. We built those data centers generally close to power sources where power is affordable. So Global Foundation Service is an interesting place to go to, take a note of, and go and take a look at the videos that we have, and those give you insight into how we run the data centers. The data centers, one of the interesting changes we had to make as we started to go on this journey of shipping on Windows Azure was actually going on Windows Azure. So Service Bus, our service, was conceived and started well before the whole Windows Azure train really started. It kind of all started in parallel. In Microsoft, there were pockets kind of inside of Microsoft where people were thinking we have to do something with data center as a service. I'm not sure whether cloud was actually a term by then. And so in 2006, 2007, all those initiatives kind of popped up across the company, where Windows Vista had just shipped. So a lot of the Windows Vista people started doing new things, and Red Dog, the predecessor of Windows Azure, was one of those initiatives. With Windows Vista, also shipped the Windows Communication Foundation and the Workflow Foundation. So a bunch of the middleware people, including me, kind of started doing new things. And all that then started to kind of gel together in the direction of building all those cloud services. Certainly steered from senior management to put it all together. So one of the putting together thing was that our service and the access control service were kind of chosen as the pioneers of actually running that service on top of the platform. So the Windows Azure Compute Service and the Windows Azure Storage Service were brand new, right? Just in development in beta. Let me turn off the distraction because you're actually looking at that. Does someone have the Jedi forces to turn off the projector? Because from this point on, we know we no longer. Nope, we can go and just. Single button. Yes, I'm sure there's a single. Yes, but it still needs to boot. Anyways.
It's gonna take 3 minutes.
Yeah, I know.
It's booting too.
I know. I can tell. That's what I said. Booting. I love it. Okay. So to make this. All right. Well, now it's already blue. So there's nothing to look at unless you like blue. So we were sent on the journey because it would be crazy to have a platform with storage and compute and all those capabilities, and then not use it. So the senior management said, well, we're going to ship one platform, so all the platforms should build on top of each other. So here we came, and we had an existing system that ran on a wonderful virtualization platform, which was custom built for us. And suddenly, it turns out we can't use it anymore. So we were grumpy. Something that will, if you're taking your steps into the cloud, will maybe be familiar, because some of those things are different if you go into a larger scale system. For instance, we were assuming from the start, we were just learning, right, that you can build a VM, you can run the VM, and the VM is going to be stable. And then you might be able to go and take a VM and restart it, and you're just managing the system as you know it. But generally, if you have a VM and you can just restart that VM again, that's all going to be fine. Your data will be there. Well, first version of Windows Azure, PaaS, didn't have that. The Fabric controller comes around and says, well, you, little virtual VM, are missing some necessary patches. Therefore, I will now shoot you in the head and throw you away, including everything that you contain. And I will then reincarnate you, however, with none of your memory, and then bring you back to life. We were scratching our head a little bit because that was kind of unexpected. So we were faced with a major replat going onto that platform, where now storage was very different, and doing that on fairly shaky ground because the storage services were not really solid yet, and the compute services were not solid yet. So that was kind of a big deal. So it was a very interesting journey. So we had to kind of go from February 2009 to effectively November 2009 because that was the PDC conference, as it was still called then. That was showtime, so we had to go from here to there in 7 months, and then you want to lock one before that, so half a year. That's the time that we had. So the first thing we did was the first thing we did.
On the board. It's on the board.
It's on the board? Oh yes. We struck the iceberg, the polar bear. We cut features. So first thing you do, you go in and then you say, of the 50 things you've built, we can unfortunately only ship 30. Because there's no way we can go and stabilize all 50 of them. That's a sad realization, that's a sad moment that starts. Then you start thinking about, okay, so what else do we need? So now we have our wonderful features, that being the relay. That's what we started with. What else do we need? With those Microsoft phones, you always think it's yours. So I was a little nervous, but I actually turned it off. Yes, everything's okay? Good, wonderful. So we were thinking, so what do we need? Well, first of all, you need some diagnostics. That's what you start with. Diagnostics is an interesting space because you never know what you'll need. We started out with what I would say from today's perspective, a fairly naive code base, where we were in fact catching exceptions that were happening, and were then one of two bad things: either handling them, but handling them in a I don't know exactly what to do here, so I'm going to do something kind of way, or worse, swallowing them. So the first thing we had to do, and this is a grown kind of startup mentality code base, because we were really coding in the beginning with like 5 people and most, and just cranking out that entire service with the website and with all the things, just with a very, very small team. So it was really, it's not the big Microsoft you probably have in your heads with 1,000 people on the project, right? It literally is sometimes as small as a small company, with the advantage that your venture capital company is very large and has ample big pockets, but otherwise you're doing that with small teams because the company doesn't want to risk all that much money on something that it doesn't know how that turns out. So first of all, we had to go and instrument all the services. So we had to go through the code and actually think about all the cases where something could go wrong, and make sure that we have all the exceptions caught and all the exceptions logged. And that's an interesting game. Once you start going productive with this, I'm going to go off the chronology actually and start talking about things where we started, and then go and carry that thread a little through. Because you start instrumenting your system, and then sometimes you're instrumenting too much, because you're actually starving out the service. If it starts going wrong, and if things start going bad, you have to think about how you actually get that data off the machine. So that's one thing I'm going to talk about a little later when I start doing diagrams, because that's actually fairly tricky. You have a machine, and if you think about single node systems, it's actually fairly simple. You go and write a logging a piece where you log. You write to the tracing API, or you go and use log4net or any of the other things. And then you simply, when an exception comes, you go and handle it, and then catch it, and then you go and write it into a log. Now let's say you have a system which has 48 front-end nodes and 48 back-end nodes. So you have 96 machines. And then you have the odd 10, 20 auxiliary things that are sitting around. And now your network gets cut. Cut in the sense that someone fumbles a config file. That happens. Someone deploys a new load balancer for you, and that kind of doesn't work that way. Someone is upgrading the database servers underneath you, and that kind of goes haywire. The fabric controller decides that it wants to kill half of your roles and not bring the rest up again. We've seen all of those things. Because we're not perfect, we're all learning. We're getting a lot better at it, but in the beginning, some things were fairly rough. If you then go and log like crazy, if you log everything that you ever see, and you write that into the files, you will find that you can't see anything anymore, because there's a lot of forest and a lot of trees, and the thing that you want is actually hard to find. It turns out that the logging and diagnostics thing is an art, because you need to go and log just enough, and that's something that I can't even give you a recipe for. You need to log just enough so that you have enough detail that you can spot an error first, So you need to go and spot the bad things, and then have enough depth in your log so you can actually go and do a trace and where you go to. You can do this by triaging or logging into different directions, and I'll probably give you some hints. One of the things that we don't have the luxury of doing is using our own things. So I can't use Service Bus while building Service Bus because that's kind of odd. It would be kind of odd. The SQL guys can't use SQL, right? Or at least not the SQL that they're building, and so that makes things kind of difficult. You want to use, okay, I really want to use the relay for this because that's actually a good thing to do direct addressing across machines, but we can't use that. So we have less things that we can use than what you can actually use for your systems. So diagnostics, that's a big one. What's important to know about the systems, how they run, and I already have this notion of the fabric controller, introduced the notion of the fabric controller, which goes around and shoots machines out of the house. It does that because all those things are completely automated. Effectively, as you're doing a rollout, a patch of a system, the way the patching works is you have, Patch Tuesday. Do we do that on Tuesday? Yeah, I think we do that on Tuesday. For me, it feels like every day because our IT folks just push an update. I connected to this network. My machine was feeling happy, and then some system center machinery, which takes possession of my machine as soon as it connects to the network. That's just one of the disadvantages of being domain joined. Said, oh, here's a wonderful patch that your machine doesn't have yet. Pushed that onto my machine. Said, you're going to boot within 15 minutes. That was half an hour ago, so I booted for a while. So usually it's Patch Tuesday. We have all kind of extra things that are affecting us. So I feel like I'm patching every day to keep corporate access. But for security patches, things that are critical for Windows, you'll notice that you have to do nothing if you're using Windows Azure. You have to do nothing if you're sitting on paths. If you have a web role, worker role, if you're sitting on websites, you have to do none of that. Party automation. What we do is, as the patches come out, actually, I think a few hours before this, we start rolling out those patches into the data centers, and then you get them automatically. It's one of the automated procedures we have in the system. We can't run the services that we run at that scale and at that cost if we don't fully automate everything. So what that means is there is nobody who will go and touch a system. Only in extreme circumstances you can actually go in and go on the machine and debug it. Something really bad would have to happen if you can actually go onto that machine, but you have to go and have to be prepared to actually be lights off and have the machine do everything it can do to help you without actually connecting to it. There's multiple factors playing a role in this. First of all, if you're running on a system that will go and is optimized for availability, you go to a machine, you run it on a machine, and the machine crashes. Or your service turns unhealthy. So it spins 100% CPU, and it spins so badly that it can no longer signal I'm alive to the fabric controller. Then the fabric controller will say, well, if you're dead, you're going to go, and we're going to bring us someone new. So now there's logging that happened on that machine, post-mortem stuff, but you can't connect to that instance because that instance is gone. So you have to have ways to deal with that without connecting to that machine. The data set, this automation mechanism and this kind of remote and post-mortem diagnostics thing goes on kind of from the bottom of the stack. And the throwing away instances actually goes that way from the bottom of the stack. So when we roll in these containers into the data center, which are either actually shipping containers in Gen 3 or these IT packs in Gen 4, watch the video, what we do is we have these racks that are sitting in those containers, and there are blade computers in those with about the same specs nominally sitting in those racks. If one of those machines goes bad, a RAM chip is bad, CPU goes bad, anything goes bad, so the health indicators on the hardware are not saying that the machine is healthy, the lights on that machine go out. Nobody's going to go into that container to go and fix it. Instead, we're going to let X% of those machines die, and then we actually take that whole container out. We're going to take that whole container out of service and either replace it wholesale or then have the vendor go and replace the machines completely. So we don't even fix individual machines. There's no individual diagnostics being done because that's too expensive. What we do is if the machine exhibits any hardware issues, it will die. It will be taken out of circulation. So that continues. If you have a bad image for whatever reason that happens, right? You have a machine and the machine crashes. The notion here and on the pass side of Windows Azure is let that thing go to hell, right? Just replace it, shut it down, replace it, bring up a new image because the new image is known to be good. So if any of that sort happens, we're going to bring up a new one. So that applies to patching and applies to any kind of circumstance when you have something go bad. Just bring up a new one. So if you need to recover information, you need to go and do that recovery of information. You need to go and save that information somewhere. So that's the reason why all the logging information, all the diagnostics data goes into storage, right? You configure a storage account. If you configure diagnostics in Windows Azure, you get a storage account, and that's where your logs go because that's the place where that gets stored and where that gets saved, and that's very important. And then you need to think about logging level. Another thing we do, and that's what we configure our machines for, is we configure our processes. We have process dumps, and we configure those. And so we have our dev team and test team is actually fairly skilled at reading crash dumps. So we have our processes, when they crash, are configured to do crash dumps, and we go and take the crash dumps before the machine kind of goes away. We go and take those crash dumps and upload them to blob storage, and we have some special tools that we use for that to go and upload them. The problem with all the tooling that I have and that I might mention is some of the tooling that we use is not ready for customer consumption. It would take forever to go and explain. It would take forever to go and document, support. So these are not products. These are just engineering systems that we run. For instance, we have a continuous integration system that we run, which is TFS, the new version of TFS, which has that kind of feature set. Certainly, those guys took a good look at the thing that we are using, but that's nothing that's necessarily shippable. So we have systems that are utilities for all kinds of purposes, including getting those dumps off the machines and uploading them, so that we can actually go and take a look at those process dumps and then see what's going on. One question.
Don't you have the same problem in the end when the CPU spins at 100%? How do you solve the problem that if the machine goes to 100%, basically it doesn't respond at all? So how do you get the logging information that happens?
If the machine, we have perf counters. That we also effectively the machine takes its pulse and writes the perf counters also onto the disk. If we see that the CPU is if the CPU is so pegged that the machine can't do anything anymore, which in case of CPU that's actually not necessarily the case. If it were spinning on the disk,
and you hit the race condition and then you just go there, right?
Yes.
And it just hits 100%. You lost the log of the race condition. So how would you be able to find it?
Well, if you lose, so if you're losing you would have to lose the entire machine with disk and everything. CPU at 100% means it's doing work, and since yes, you will have one process which is going to be very busy, but the other processes also get some airtime as they're doing things.
Unless you get killed by the fabric control.
Exactly, but then you're spinning down, and well, sometimes you end up in a situation where you don't have any traces.
Okay, so
and then
that's
so that happens. That happens.
Something that you live with.
Okay. Yeah, we got to live with that. Yeah. So diagnostics is the first field which is really important because you need to have eyes in the system, and you need to be. And it's not that you can walk up to the machine at all times and basically just go and say, okay, so what's wrong here? We do that sometimes. If the system is kind of somewhat unhealthy, we might actually go in and take a look. We typically only do that in test systems, though. We rarely do that in production systems because there's another catch here, and that is we don't run the systems as a team. Our product teams don't run the system. We actually have other teams. We have an operations team which runs them, and then we do that in cooperation. You can't, me as an engineer and the product group, I can't touch your operational data. I can't do a database query against the operational system. There's a kind of a firewall, and all of the guys who run the system can actually go and do that. So if we have questions about how those things work, we actually need to go to the guys who run the system, who then we can give them a query and say, go and run that query, and then give me that result. There's always separation between those. So diagnostics is that's a tricky thing. Next one is usage. Usage means, diagnostics means you have to understand when something goes wrong. And yeah, let me back up before I get to usage. So when something goes wrong, actually there are things that go wrong. Do you still see me?
Yeah.
Okay, good. Just making sure. There are things that might go wrong that may go wrong from a customer perspective, that may go wrong from a technical perspective, but that are probably not worth logging, or at least not logging at a very high level. So I'll give you one example in Service Bus. If you come to me, and if you come to Service Bus and you make a connection, and then you cut the cord, so you effectively do a connect, and then you abort, you just walk away. What will happen is, since parts of our feature is sitting on top of WCF, they will spray a fireworks of, oh my God, my connection broke events around them. We don't care, because cutting a socket is normal. It's just fine. We do log that, but we don't log that in any way that it raises anybody's attention. In the beginning, we did that, and that is not a good idea, because then your support people, the people who run the system, will come and say, what is this? Something terrible happened. The customer had a bad experience. Well, no, not necessarily, right? If they are on a wireless network and they're kind of in and out of the coverage area of the wireless network, yes, they will lose the connection. That is normal. That's just part of the operation of the system. So not everything that is an error or something that goes bad is necessarily something you need to go and catch. What helps on the other side, that's something that we're Microsoft, so we need to be careful about those things. What people do, what I see people doing, and that's in a solution environment easier, business solution environment easier than the platform environment, is to use telemetry from all sides. So if it was my choice, if I was at liberty to do this, I would go and make the client log everything and actually upload its data. So if it sees something that's bad, it should go and simply take the data that it sees, any exception data that's kind of out of the ordinary in terms of connections, etc., and just throw that onto a bucket on the server. Because you actually need to have both sides. So today what we do is, see, if you raise a report to us and you say something happened, we have our tests. I'll talk about that too. We know just about how your experience is, but we can't exactly reproduce where you are and what your network sees and what your circumstances are. So whenever you come to us and file a bug report or have a support request, we ask you for details like traces, .NET traces. We ask you for stack traces and all those things, because we need eyes on your system kind of to help you figure those things out. If I was building a business system where I wasn't under constraints for privacy and the platform is snooping, etc., I would actually build that in. I would collect all the data and actually go and put that into the system. We do some of that, if you agree, in a number of products. Windows error reporting. Well, that's exactly what that does. So that's a good idea to build into systems, kind of not only the server side logging, but also the client side logging, to kind of catch the data and then put that data into a store. One of the things that we do as we do logging, I keep in mind that I was actually wanted to talk about usage, is we have causality IDs. The causality IDs is something that we flow We originate them on the server because we don't have that end-to-end flow. What you should do if you're building a business solution, you have a client that's active, like if you're building a Windows 8 client or an iOS client or any of those things, and you have secure connections. The causality ID, how a request hangs together, is something that you can go and very easily originate on the client, just make a GUID, and flow that with your request. It doesn't need to be GUID, it needs to be some identifier. The great thing about this is if you go and write data into the logs and you have effectively your ID that you flow in, your context ID, flows around with all the operations that you do, everything that request touches, and you log things as they're going bad. You can go and correlate them and effectively in postmortem figure out what originated here on this client, because you're collecting the logs, has caused this error to happen here and this error to happen here, and you kind of get a flow through your system. If you take all the logs that you take in your system and kind of flow them into a log repository, and you make that causality ID a key that you can actually go, a bucket that you can follow through, you can actually you can pinpoint after it happened all those kind of the flow, the errors that caused that issue. That can pop on the user's screen, or sometimes, and it does so on web pages, if you see these error IDs, we also have them in Windows Azure. We actually do that in Service Bus. When we throw a fault at you, you get a tracking ID in the message text. That tracking ID is a key into our logs, and we can actually go and see exactly all the things that had to do with that particular operation. So that's a very good thing to do. Either you flow it straight from the client, or if you're just doing it on the web, on the back end, if you're running a website, it's a very good idea to take that kind of a context and kind of flow that context along a context object as you're doing those things. Yes, it's ugly, right? If you're a fan of the beautiful, wonderful object-oriented API with the pureness of the business model, blah, 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 all those things. Yes, it looks pretty ugly if you take a utility object that has so much nothing to do with all the beauty of your domain world, but it's pretty useful. So that's effectively the object that you're passing along is the object you log to. It's the tracking context, as we call it. So you take that tracking context, you stick that into all the things that you flow along, and then also that object you log on. And that makes that fairly easy to deal with. Usage. So far, I've talked about things that are going wrong. Now let's talk about things that are happening. Usage is an interesting field because usage, there's so much happening in usage that you can't even get this stuff off the machine. If we assume that for our diagnostics that most operations go right, that let's say 99.9% of all the operations that you do are actually going as planned. That is a good goal. Right? Our system starts screaming at 95% for a very short time period. That's when the light's already red. And what we're aspire to is 99.95% of perfect reliability happiness. So if only so few things go wrong, that's already causing a lot of traffic. Now usage, now you have to go and track everything. Because you want to know what everybody is doing and how people are using your system. In the case of Service Bus, we want to know how many messages you send. We want to know how many bytes you send, how many bytes you receive. We want to know how many queues you create, how many sessions you make. We want to know everything kind of that you can do as a gesture in the system. The reason why we're counting that is because ultimately we need to write you a bill. That's not billing yet, right? So we're just having effective telemetry usage of the system. It actually turns out that's a very, very useful, just separate from billing. That's something that's an enormously useful thing. We actually get that data, we use that data in a roll-up, and that's a key word here, in a rolled up and anonymized form to see how people are using features. And so we have, for instance, a feature that did we announce that? We might deprecate that feature. I don't know whether we did that already. Sorry. So if we wanted to deprecate a feature, which I always think is a bad idea, but anyways, we can go and look at the usage data and say, how many people are using that? And if we find that we only have 15 different tenants who are using that, we can go and say, to go to the people who have the keys to the castle and say, hey, can we get the contact email of those 15 people? We'd like to give them a call, which we actually do, and say, would you mind if we turned this off in a year? And we'll actually help you to get off that feature to get into the new feature, which has the same kind of capabilities. So sometimes we do this because that informs whether we leave you kind of in the dark if we go and turn something off. So we want to have visibility into the system of how you use that. And also, what kind of features are popular or not. If you have followed the Building Windows blog, as they were building Windows, there was a lot of heavy reliance on telemetry information based on what people were doing with Windows. And when you consent to participate in the user experience program, that's kind of what they do. The UI of the shell is instrumented, and they're effectively tracking all the things that you do. And also in what time interval you're doing some things, or you're doing this, and then they're running the clock and they're kind of seeing what you're going to do next, so they can do all those things. They're effectively tracking all that information, and then they make a handy package and upload that. That's what you consent to when you're consenting to the customer experience program. That's enormously useful when you think about building Windows 8 applications, for instance, or iOS applications, or any of the applications, native applications which run on the device. You make some funky design where you say, this button here, you have to go here first, and this button here is not so important. And so you make some decisions about how you anticipate people using your app. Maybe that's not right. Maybe people are using your app differently. On web pages, we do that all the time, right? On web pages, there's A/B testing. There's, we're measuring. We're showing you a page. We show you the next page. We're measuring how many people are actually staying on that page. There's all kinds of things you can measure about people's behavior by how they're interacting with your app, what they touch, etc. But you need to go and capture that data and put that somewhere, right? So that's also part of the usage story. So we have a usage story on the server for my service. Other services have a usage usage story that's somewhere else. What's common to all the usage tracking stuff is you can't do it. You can't go and track the data in real time because you can't do it. It's hard to actually go and get all that data off the machine. It's like telemetry from any other source. Let's take an example from an engagement that I've been pulled into from earlier this year. So there was a machine, an industrial machine manufacturer who wanted to take raw eventing data that came out of their industrial machines on the factory floor and push that straight into Service Bus. And they had done some preliminary testing, and they said, well, you're a little slow. For our needs, you're not fast enough. And it's a terrible thing, and blah, 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 blah. And then I did the math, and I said, look, if you were seriously doing this, you would have to have 5 gigabits upstream per second from your facility, your customer facility. Do you have that? No. Not surprised. So you can't get that data off. You can't get that data into Windows Azure without having that 5 gigabit uplink with the data that you gave me. Well, what shall we do? Well, you probably need to go and reduce that data a little bit. You probably have to do some roll-ups. And that is what you need to do. So you are going to collect some data, but you will have to make some trade-offs, and you will have to go and do some roll-ups. And that's what we do in our system. So in the system, we're measuring usage, and we're measuring usage in buckets, and we say we have per entity, in our case that's a namespace, in Service Bus. We have that's our notion of tenancy. We have n different kinds of counters, and the only thing we can do in usage is we can go and take special events, and otherwise we can go and do averages and then go and collect the averages. So on every machine that we run, we have buckets, and you take the pulse of all the components that you have, and then you go and roll the data into buckets. And you kind of keep that bucket around in memory for 5 minutes, 10 minutes, however long you want to have it. And yes, you're going to risk losing that information when you're losing that node, because you're keeping that data in memory. And that is perfectly fine. You need to figure out what are your timeliness requirements, how timely do you need to be, and then you need to. So timeliness is one of the aspects, and then certainly how much can you risk losing that data. Usage. So that's usage. So usage is something that is an aggregate of information that is being generated on the individual nodes, and only the aggregate flows out. In diagnostics, you have to flow the details, because you have to know. But it happens more rarely. In usage, you have to go and you can't flow it all, because you need to have all the data, but you can't get all the details of the node, or at least it's very hard. So you have to go and do some kind of aggregation. At least if your system is very busy, right? And you want to have that system very busy. Billing is something that's unique to us, but if you're running a SaaS system, it's similar to what we do, you might want to do transactional-based billing, right? You can do something like Office 365 does. You can do a monthly subscription, or you can do transaction-based billing, as we do it in Windows Azure, depending on what you do in this system. So that feeds, so your roll-ups, your usage information, feeds into billing. Now, what are you going to do with billing? Usage translates somehow into billing. So you take your usage and you take your attribution of that usage. We're going to get to the attribution and how you do this in a moment. You take the attribution, what does that usage belong to, and put that into the billing system in billable units. So there's some amount of translation, but there's no money that's being associated with that, because that would be fairly crazy. The systems don't need to know about money. The billing system needs to know about money. And so you take there's a usage stream and there's a billing stream, and that billing stream gets collected separately, because only some counters that you collect in your system, some of the usage counters actually count towards billing. The billing data, again here, you got to go and collect. And if we're collecting the data and we charge you by per message, as we do, and you are sending with a super high rate, right, of tens of thousands messages per second across multiple entities in the Service Bus namespace. Again, we need to go and do that roll up, so that comes out of the usage data. And if we lose a node, we know that we might lose 10 minutes worth of billing data, but that's fine. Underbilling is okay, overbilling is never okay. That's the philosophy here. So there's usage information goes into the big usage bucket for analysis, and there's billing data that goes into the billing pipeline. So it's effectively the usage data gets repurposed for the billing purposes. All right, so that's a glimpse into some of the data types, some of the infrastructure that we have for just flowing data out of the system. Another piece of the infrastructure, another interesting one is, and it's related to this, is provisioning. Provisioning is an interesting piece, and that is easily overlooked. And once things get more complicated, it actually becomes kind of a thing. So you walk up to the Windows Azure Portal and say, I want to have a new Service Bus namespace, or I want to have a new cache, or I want to have a new access control namespace, or I want to have a new storage account. You push a button, in the list comes here's your new thing, activating, spinning balls. The spinning balls is actually just an animated GIF, but it looks good. That's the evil thing about those things, right? They just give you a graphic. The graphic just sits there and entertains you. And it implies liveness, but it's just a trick. Anyways, it's entertainment. That new, the new HTML portal, I think they might actually do that without a GIF. I haven't even looked, but I think they're just tricking us. So it says activating. At that point, a few fairly interesting things need to happen because we have 8 data centers. And there was a drop-down box that said, pick your data center. So where does that data go? What happens then? Well, what we need to do is your new namespace that we create, Fred 2473, that might be available, .servicebus.windows.net, at least it was available until the internet people who are watching now pick that namespace. I forgot the number. That namespace, if you create this, it will be placed into the West Europe data center. So what we need to do is we need to go and take the name that you chose, and you need to bring that into the West Europe data center. Now make a few things. What we need to make you a bucket in the system, which means we need to tell that scale unit, well, if you see a request for this particular namespace, that is legit. That thing lives here. And then we also need to make you a DNS CNAME that will go and point to our deployment CNAME. And with that, you can show up with that name, and then we know where you live. So there's a number of steps. We also need to go tell ACS, in our case, the access control system, hey, there's someone who's new, please make an ACS namespace that's matching that. Make a new owner account, give that owner account a key, do all those things, and then give me that data back so I can report that back to the user. So there's a number of steps. There's a workflow that happens on the back. Another thing we need to write. So placement, if you write a multi-tenant or multi-user system, there's actually a thing on the side, a basic of your system that is a provisioning service, which I see as a concept popping up all over the place and all the time. Another case for a provisioning system, for instance, is if you have devices. Now I'm thinking about a service that you could know that's available here, because I haven't looked around all that much. So in the US, there's Netflix. Do you know Netflix?
Yes.
Yes? We don't have that here, right?
I can tell you how you get it.
I know how to get it because I have it at home. Yes. Look, I'm a network Jedi. They don't stop. But now they know. That was stupid. I also have Hulu. So if you have one of those online services, what they'll do is you can go and tune in on your XYZ device, on your TV, your Xbox, your whatever you have, and then you can go and connect your device to that service. For that, you also need to have a provisioning step. You effectively need to go to a portal. The portal says, who are you, blah, 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 give me your money, your credit card, all those things. Log in. Here's a code. Put that code onto your device. The device, now you put the code in. The device connects, and now they go and pair that. That's not part of the operational part of the service. That's just that's a provisioning step. That's an extra step to actually go and get things going. So that provisioning system is something that is a key piece. That provisioning system also needs to be fairly robust, and that typically runs a workflow. So running it's a long-running process. Things may go wrong, and they will go wrong. So building something that is a fairly robust thing is actually a good idea, because there's a scheduler agent supervisor pattern that I have on my blog that I explained there, and that's exactly was born out of the provisioning system, which takes your job and executes it. So what it does is, that's an artifact out of when we built this. I had to build my own kind of little workflow state machine for that purpose. And so you give me a job, and the job is make me that namespace. The system will relentlessly keep trying to build that, to make you that namespace. And it will try and try and try and try, and it will assume that it will never give out that job. it will assume that your job is legit, and it will also assume that the system is perfect, and the system makes no mistake, and that anything that happens on the way must be an intermittent issue. And an intermittent issue also counts that there's a severe bug, and someone needs to go in and write a patch and go and update the system to actually then be perfect. But it keeps going and going and going. It's self-healing, because we can't afford that whenever something happens in the hiccup, the DNS system doesn't take your record, that someone needs to go in and fix it. No, you just make it relentless. You try again, and if the DNS system says 400 times, sorry, I can't make that record, keep going. Maybe you sleep, maybe you slow down, but you don't give up that job, because that job was given to you. You have to execute that job. So you go and fix the system around that job if it needs to be, because there's a good chance that if one job is exhibiting that problem, there's another 1,500 jobs which are exhibiting that same problem. So if the way you hooked up your DNS system is wrong, well, then you keep those jobs in the system. You don't abort them, but you rather go and fix your DNS thing.
So how many jobs do you get red lights?
We get red lights after a job has been around for a while.
So it doesn't matter how many, but how long?
Yeah, because intermittent issues are normal. Like that's another thing that you find out. There are things in the system that we're actually fairly open about. For instance, let's take SQL, the SQL database. The SQL database is a multi-tenant system, and if someone overutilizes the database system, if the database node gets overutilized, which means it gets under enormous stress, the system will go and start defending itself by lowering the amounts of transactions it can take. So it's going to start throttling. Because it needs to go and defend itself in some way. Because SQL is a combination of compute resources and storage resources. So it needs to go and start saying, hey, slow things down because we can't take that load anymore, but we want to keep everything transactionally consistent. So they'll do that. Well, but you need to be able to live with that inside of your system. So it is okay if a storage operation goes wrong. You just have to live with that fact. And if that happens, well, then you go and say, oh, you take the pressure that you get and accept it, and then maybe you try again right away. Maybe it's just something was a hiccup. And if that doesn't that doesn't work, well, within an allocated time span that you give for your operation, maybe that's even a minute, you start backing off a little bit more, but you wait until you actually get that done. Don't give up after the first time. Go and retry. That's perfectly fine. That's a good thing to do.
So it's basically eventual consistency or enforcing. So
that has nothing to do with eventual consistency yet. If you get a job and you get some work, and let's just say write record into a database, right? You get a job and you have that job is in flight. You get an HTTP request. The HTTP request comes in. As far as the client is concerned, that operation isn't done yet, and the transaction isn't closed yet. So now I try to write it into the database. I can't reach that database because as it happens, your database node just failed, and it's just doing the failover switch to the secondary. Because that might happen, right? If you do millions of requests, then you will catch that moment at some point. So now you are in a logical second or 2 seconds where that happens. So now you're hitting the dead database, which is just being taken out of commission, right? Because that's what the network infrastructure still thinks you're doing. So now your operation fails. What you'll do is you're going to get an error, and instead of failing back to the client, you say, no. My operation has a timeout of 30 seconds or 60 seconds or however long you want to make it. But give yourself some time and let's go and try again. Don't give up and stand there for your customers, for your clients, and put some smarts into the system so that it can actually deal with failing resources, because you have to. Not automatically whenever you do an operation and you get a failure, that means you've got to give up. Because you need to know in your system that the resource you're going against can fail, because it will. Because it's inevitable that if you run systems, if you write systems that are up, when you aspire to 4 nines, right? We're not there yet, right? If you notice our SLAs that we give you, well, actually, it's not true. We're there, but the SLAs that we can give you, right, are not there yet. So if you aspire to 4 nines, well, there's 0.01% of transactions that will go wrong, right? In both reliability and availability and all those things, there's stuff that will go wrong. It's a game of very many successes, but also failures, so you have to deal with those failures. So that's very important. Whenever you write a distributed system of any kind, you have to be tolerant of failures. Yesterday was a great example. Not bashing the competitors in any way, but it was a moment of, really? Gmail went down. Portions of Gmail went down. It is impossible for Gmail to go down as much as it's impossible for Facebook to go down. Let me get to that in a moment. As I start drawing. So far, we haven't done much with whiteboard yet. But then also, people whose Gmail was down saw Chrome crashing. Because it turns out that Chrome interacts with Gmail, the browser. And they apparently have some interactions where, well, if the service isn't there, and so if internet is available and the service isn't there, Chrome will start crashing. That's fairly crazy. Don't have that, right? Just don't have dependencies like this, which are unmitigated. You have to go and if you want to get rid of that, if there's data you gotta get rid of, well then retry, or have a way to go and give up. Or write it locally on disk. Do something. But that's something that's important for reliability, yes.
And the whole thing is like, the whole execution of the task is like a big task that is then split into multiple asynchronous tasks, or is it like after one sequencing and then asynchronous, or how that goes?
Our world is entirely asynchronous. Everything is asynchronous.
So basically you have the big task and then smaller tasks that they execute and they...
Stuff happens in sequence, right? But it all depends on what you do. So in our service, we have the advantage. Actually, that's probably a stupid statement that I was about to make. Most services that you build in the cloud, most backend services are doing a lot of I/O with a little bit of compute. Most. Then there's some extreme ones which are very compute heavy, which are rendering and all those things. But most things are really I/O intensive. Most web apps that you write are database editors, right? Very funky, wonderful, colorful database editors, but they're database editors. Or the fanciest ones are actually database readers. But what they do is I/O, right? They take some data from a database, mash it together with all kinds of funky graphics, and throw it up. So they're doing mostly I/O with a little bit of compute, except for the supercompute heavy ones. Async is required. So just to give you data, because you were going on async, and I'm happy to go onto a tangent today, I will speak until the last person leaves the room and is fatigued.
Be careful because I don't have a watch.
I know. Yeah, I'm going to eat my words, I think. A glass of water would be great. If Katrine, thank you very much. I didn't know what to send you though. But yes, I did actually. AZUG, yes. So we shipped our first version of Service Bus, our first, the bits that went into the data center in November 2009 were factually, except for the billing pipeline, the same bits that actually went production in January 2010 we were there. So functionally, that was the same bits. We spent effectively the next 2 milestones doing nothing but doing a conversion of every single path that we had left, synchronous to asynchronous. As a result, after deploying the second update, and that was probably 5 months after we shipped, so kind of in summer, We did some other work too, but there was not a lot of feature work there. And that's the pay. When you work in here, and everybody's looking at your shiny bits, it is enormously painful because you're sitting here and you're working on all that debt, and people are saying, "What are you doing?" Like, I can't tell you. Because depending on how bad it is, you really won't tell anybody. So that was one of those parts. So we spent probably a good 5 months converting, amongst other debts that we had accumulated on the race to shipping. But that was the biggest piece. We converted all the remaining synchronous paths to async, with the result that we were able to turn off up to 2/3 of the nodes we were running on. Same capacity. Async is an enormous advantage when you're running in the cloud. And actually, personally, I think the .NET Framework 4.5, that is the framework version for the cloud. Nothing before that. Because it brings you kind of a programming experience from async that is understandable for normal human beings with this async and await model. There's some weirdness there with you have to return the task object, etc. And so I think that could have been made a little prettier. But I think it's getting close to being ideal. And what the framework does, what the compiler then does, is it sees those keywords and shreds your code into the necessary callbacks and all that stuff under the covers. But it gives you a normal look and experience. There is really, at this point, if you take the 4.5 changes with async await, plus all the changes that were made in ASP.NET, and all the changes that were actually also made, for instance, .cf also supports that task API, right? Not dead, they're actually working on it. And Web API is supporting that now. There is no excuse. There's no excuse for keeping synchronous code in your code bases. Not based on this is too complicated.
You can use version 4 with the async pipe as well. So
yes.
It's not only 4.5; it's 4 as well.
Yes. So it is really enormously important. Why is that so? Why is that so important? When you build network-bound applications, HTTP with the database, your machine mostly spends time waiting. It spends time waiting for stuff that comes down the pipe, or that goes up the pipe, or that goes to the database from the database. Otherwise, your machine is effectively idly hanging around waiting for results. It doesn't do anything. It is crazy to have all these threads kind of sitting there in parallel, consuming memory. What is a thread? A thread is a stack, memory, with a set of registers, all that stuff, sitting around there, sitting on an operating system log. An operating system log is an object that needs to be managed by the operating system. The operating system needs to kind of go and check on it in various ways. Well, and that thread sits around in the operating system, which needs to be managed. And the scheduler needs to know about this. You're putting enormous stress on the system, just on the scheduling side, but also because you're having all these stacks sitting around that are sitting on those log objects, you consume enormous amounts of memory, which is terrifyingly bad if you want to create high density on the machines, which means you don't want to have a lot of nodes. Because if you have a stack sitting there and the stack says 2 megs deep, well, you can't have that many stacks sitting on your system. So you want to avoid that. And by using async I/O, the async programming model, and you're hitting async resources, you don't manage any threads because the operating system does that for you. So in Windows, there's I/O completion ports, that's the underlying mechanism, where the operating system is managing a pool of I/O threads. And all you do in an async model is you say, please do this, begin receive on a socket, and you provide a callback, and you say, try doing that, and when you're done with that, call me back on that callback. That callback is getting called on the thread that's being handed to you by the kernel, effectively. That says, hey, here's a thread that I've just made into a user thread for it. Go and do whatever you need to do, and then give me that thread back. So that's handled by the operating system. That pool is shared across the consumers, and you don't have to manage those. And you don't put a lock in there. If you put a lock into an I/O thread, then of course that thread pool needs to grow, and it will do that. But it's effectively like cooperative multitasking. Who still knows Windows 3.1? Raise your hands. Who has programmed on Windows 3.1? Great, good. So you guys know how that is. There's one thread. Let's take the network version of Windows 3.1. Who knows Node.js? It's the same model, right? It's cooperative multitasking. You go and yeah, that's going to get me fired. No, not fired. It's going to get me into the fire. Now the whole I can see Glenn Block getting the pitchfork out and dusting it off. Well, but that's actually the same model. What they do is they create one thread or one process, and now all the application threads that you have, or sort of logical threads that you have, actually run out one process, and everything is happening with a callback. And the JavaScript programming model is actually lending itself towards that, when you do little pieces of work, and then you hand off control via a callback back to another I/O operation, and then you get called back. And actually, Node.js it's beautiful because it's all async, and it'll give you a way to do it synchronously. So that's actually a very nice way of doing that. And so the .NET framework gives you a way to do things synchronously. Arguably shouldn't. And if I could break it, which I can't, I would force every synchronous operation to be called read sync and write sync, and make all the async operation be undecorated and be read, returning a task. Because that would be the right way to do things, knowing what we know. So async is something that is enormously important if you want to have high density, if you want to have low compute costs in Windows Azure or on EC2, wherever you are, wherever you want to go on your own machines. You need to achieve high density. You need to get a lot of work jammed into one machine, and async being enormously greedy on threads is one way to achieve that. Because that stuff burns a lot of memory, and it also makes the operating system do more work, so make it asynchronous. So, I said I will be whiteboarding, so I will be whiteboarding. Let me give you, this is where probably the team in Redmond, if anybody caught that tweet, Abhishek may be watching. That's one of my PM colleagues. One of the mistakes that's being made when people talk about Service Bus is that they say Clemens is Mr. Service Bus, and he has invented all those things. It's not true at all. We're a fairly large team. We have a bunch of PMs, and I'm one of the guys who they come to and say, "Hi, how do you think about this?" But really, the other guys own the feature. So Abhishek, for instance, owns the API, and he might be watching this because he's also a Twitterer. So that's the moment where the team shivers, because now I'm going to spill the beans on how we actually work.
Actually, how large is the team?
The team size is hard to quantify, so therefore I'm not going to say that. Because, well, no, but
There's 7 now instead of 5.
yes, no, we're a few more. It's hard to draw the line. That's the point. Because we have we have user education people who are writing the docs. We have people who are building the code. We have people who are helping our largest customers with things. We have people who are answering calls in the support desk. And if you count everybody and everybody who touches Service Bus, it's very many. And it's probably unfair to draw the line right around the triad, the dev, test, PM, because there's a lot of people have to do with that product. And if we were operating this as a standalone business, it'd be more. So I think any number I could tell you would probably be skewed one way or the other way. So I'm not going to say that. we have more than 50. Right, so that I'll say. We have probably less than 500. But there's, between that, there's a lot of numbers you can think of. And I would not even say it's closest to the one than to the other. It's all a matter of perspective. So, Service Bus. Who knows Service Bus? That is wonderful. I have the true friends of the middleware. Some of the friends of the middlewares are actually in Redmond because there's the BizTalk Summit, which is a wonderful thing because it shows you if there's a BizTalk Summit, there's BizTalk, and there's something that's worth talking about. So that's a beautiful thing. It took a long time for that to happen. So now the BizTalk people who have kind of their careers invested in BizTalk are starting to believe it too. So there's going to be a next version. I think we actually have the beta of the next version kind of already available as a VM in Windows Azure. So that's great. And since we have a little bit of time, I might actually talk about the relationship between that and Service Bus in a moment. So to complete this piece about running the system, let me talk about some structural things in the system that we have, kind of from an architectural perspective, because it might be interesting too. So we effectively run the system with 2 roles and some change. So I'm talking Windows Azure worker roles, in fact. So when I say 2 roles and some change, there's probably 5 or 6 roles that we have. Some of those things are auxiliary, right? I talk about provisioning. So in each data center, in each scale unit, so that's what I'm going to get to. In each scale unit, we have an agent, and that agent is kind of the local, the guy who looks after what's happening in that scale unit. So we need to have a process that we can go and talk to, and that's unlike the others. There's another guy that looks after our scale fabric. That's kind of the mother of the scale fabric. Talk about that too. But the vast majority of the workload is being done by the front ends and the back ends. The reason I'm telling you that is not that I want to tell you all about our internal structure, but because that's actually a very useful split for your own systems. The front end, and not surprisingly, that's something that we've been doing for a while, because there is user interface, right, and business logic, multi-tier. Check that out. So it's not that I bring you the revolution, but I bring you probably the evolution of the revolution. So this is our presentation tier, if you will, and what we present to the user, to the outside world, or a messaging engine, is we put stuff on the wire. Sometimes it's markup, sometimes it's not. Sometimes it's NetTCP binary, sometimes it's now new AMQP, Advanced Message Queuing Protocol 1.0. But it's stuff we put on the network because we're all about network. We're networking stuff, right? Other services like SQL, a SQL database in Windows Azure, gives you TDS, right? The tabular data stream, that's the SQL protocol. That thing is what I call the gateway. The gateway, and so when we have customer engagements, we actually start talking about the gateway, is a set of nodes whose primary job it is to talk to all external clients. A website, in that sense, is a gateway. And sometimes it's okay for that gateway to kind of be lumped together with its logic, if that logic is fairly light. If that logic is more compute intensive, needs to do more work, if the work probably takes a little longer, then it probably makes sense to go and have a layer that sits behind this, and that is the let me call this a workload layer, or the backend. So let's say you do, you encode videos, right? So we actually have a custom-made backend for this called Windows Azure Media Services, but let's say you want to build your own. Well, you come in through the gateway, and the gateway is now concerned about one thing, and one thing only, having enough scale to deal with your uploads and your downloads. And that's what you optimize that thing for. You don't optimize that thing for doing the number crunching and all the things you need to do to go and to make the processing fast. That would be the wrong pivot. What we need to do here is you need to go and make it such that you can actually go and manage the bandwidth that you need, and manage the connections that you need here to go and get that data in and get that data out. Likely get that data out. So you have a different pivot here in the gateway than you have in the backend. Same thing is true for our system. In Service Bus, for instance, the gateway is concerned about managing connections and managing very many of them. Every connection that we manage, may that be HTTP or TCP, consumes memory. Consumes memory because TCP has a receive buffer. And when you think about this in a normal system, that's all fly shit. You don't care because it's 64K. 128K. Who cares? Well, if you have to manage tens of thousands of them, it actually starts to matter because that eats a lot of your memory out. Actually, the majority of it. So all those little things start to count. Turns out, so let me talk about a gateway, and let's talk about a hypothetical thing. Let's say you want to manage connections to devices. A few. 10, 15 million. You start laughing. If you're working for a car company, or if you're working for a consumer electronics company, or if you are working for a company that makes washers and dryers, those are numbers which sound good because that's how many things you make. Turns out, a lot of those people who are building those kinds of consumer-oriented things have now started to use the internet for all kinds of reasons. For instance, telemetry. So the device itself says, I'm happy, everything is fine, that's what you want to hear. Or it says, I'm kind of cranky and my filter over there kind of has a little bit of an itch. But it's working okay, but it could be working better. So you have that kind of telemetry. That's great, and we see many customers starting to show up and say, hey, I want to do predictive failure analysis. I actually want to go and start doing light telemetry from my devices, hook them up to the wireless network so that we can see how they're doing. Let's say you are making, and I have to make the cases slightly silly because we actually have, if I say the device name, then you could be closing in on who the customer is, so I'm going to make this something else. Let's say you are selling industrial toasters. No joke, or well, sorry, not industrial toasters, but for hotels and restaurants, you're making toasters. You might be familiar with those kinds of toasters that are in the breakfast room of a larger hotel, right? You take the toast, put that on that thing, and it rolls in, and that kind of drops out half toasted. So you got to put this in again. Those kinds of devices. That's what I mean, right? That's a hotel quality level toaster. Let's assume you are now producing those things in large numbers. You are the world market leader in hotel quality breakfast toasters. No joke. I mean, there are people who are market leaders and so you sell tens of thousands of those things. And I can tell you, something that's terrible is that if in the morning that toaster is not working, unhappy customers. You don't want to have that. Unhappy hotel customers, worse. Because if you don't get your toast, it would be worse if the bacon wasn't there. But toast is fairly terrible. So the world market leader in business toasters, says we want to introduce predictive analysis and actually go and feed telemetry into our systems and see how the toasters behave and how all the metrics are before a toaster fails. So they start doing that. And we see customers, not with toasters, but with other things, doing that. So they are trying to instrument their devices, and they're spitting out data, and they're looking into that data, and if a device fails, they're going to look into the history and say, how did that thing behave? So that they can predict when that happens, so that the customer service agent can actually stand in front of the door with the replacement part days before the device will fail. So that happens. The next step is then to go and also control the device remotely. That's the next step in that, because if you have a network connection down, well, then you probably also have a network connection up. Now, if you think about that in scale numbers, and what you need in terms of connections for that kind of telemetry, when it's more than a toaster, but industrial devices where it's vehicles that roam around the street, you think about putting telemetry into a bus, telemetry into a train, telemetry into all those things, then you probably have to go and maintain all those connections, and then that becomes a thing, because that is now occupied with just doing connections. And it shouldn't be doing anything else. And it also needs to do things like, doing usage metrics and doing all kinds of things that only have to do with connectivity. So having a dedicated gateway role is a good idea for many services. That's why we have one. And then you have some workload things that are sitting in the back. So for instance, our messaging system, if you install Windows Service Bus for Windows Server, Service Bus 1.0 for Windows Server, you're effectively installing a somewhat cut down version of our messaging backend, that thing that we run in the back, and that is our broker. So we run that broker engine that you can download for free and install, Service Bus for Windows Server. That is the thing we run in the back end. Actually, in a very similar configuration, except that the configuration that you get, and that's merely a test constraint and not a constraint of us not giving that to you, we will give that to you, is that the thing you can install today is a 3-way cluster that's interconnected with a fabric, or with a back-end scalability fabric that will have a primary and a secondary and another secondary for each queue or each topic. And if you shoot one of those machines out of the sky, then they're going to elect another secondary. Effectively, they're going to elect a new owner. You can actually try that out if you run Service Bus for Windows Server in a 3-way cluster configuration, also with a 3-way cluster configuration for your SQL Server, and you are running them into physically separate machines. You could actually go and just turn the switch off onto one of the machines, actually 2 of the machines, and the system will keep running if you configure it as per the guidance. So we do that in the service on slightly larger scale. We do that in tested configurations of n machines each. I'm going to get to that in a moment. And that's the primary workload that we have in our system, and that is doing messaging I/O, kind of dealing with specifics of messaging, putting data, filtering data, storing data into the database, getting data out of the database, doing prefetching, blah, 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 all the wonderful things that we do in the back. All the features that we have are sitting in the workload service. Similar for a lot of things that you do. Sometimes work is very lightweight, where you're effectively getting a request and you're just turning data, you're just turning the requests around and say, here's some markup, and go and take all the auxiliary stuff, pictures, etc., from the static store that sits over there. And then you don't need that, or you have operations that take a bit longer, that have a different bias, and they might work on a different node. So actually having that split between web and worker role in Windows Azure makes a lot of sense once you get into very specific kind of, once your system has a specific bias and a certain scale. So we are at the point where we actually have that scale, where we need to have that bias in the system, where we have something that is focused on communication, we have something that's actually focused on doing the back-end work. So we're splitting that in roles, because the VMs are actually doing different things. The memory we have in that front-end role here is occupied by doing communication stuff, and the memory we have here is doing other things. Scale is an important aspect. So the way we run this is in very well-tested click stops, if you will. And I'm just going to give you some numbers. They don't need to be, they are not meant to be accurate for what we have. Let's say 4, 16, 4, 8, 16, 32, 64. By, depending on what the bias of your system is, right? By 2, 4, 8, 16, 32. It's not necessarily how we run this, but it's kind of an idea. This means the number of concurrent nodes that we run. Notice there's numbers missing, right? My daughter, who's 5, would start spotting this and say, "Daddy, that's not right." So these are the click stops. Now, we don't use auto-scaling in the system. We find all kinds of really weird behavioral changes once you scale up, and as you learn running your system, some of them will surprise. Where you have a system that runs perfectly fine at 16 nodes, and it ought not to have any specific scale constraints, and then you run it at 48 and it keels over in wonderful, colorful ways. Stuff just starts going wrong because you missed something. It is fairly crazy to go and start with a system and start testing it on 2 nodes or 4 nodes, and then put some scaling policy in that thing, kind of an automatic robot which goes and looks at some parameters, and then goes and says, let's go and make 32 nodes, because that's not going to work. If it does work, you're either extremely lucky, or you're just serving up static files, and you probably should be serving that out of the blob store. But that's something that's not working. That's not going to work very well. We are enormously disciplined, and that is something that we have I would say our true superstar that we have in the team is his name is Cesar. I'm not going to say the last name because I don't have permission for that. But so Cesar is our test manager, and Cesar knows truly how to torture a system and torture it into submission. And he is an artist in doing that. The test team, so we have dev, test, and PM, right? The test team, our test organization, is a peer of the development organization. There is no, developers kicking the testers around. The test organization has its own pride, and is an organization that does testing, and it's good at testing, and they know exactly how testing works. And when I say testing, I don't mean unit testing, right? Unit testing is something that the devs do. Test is something that the testers do. Testing means you break it, and you know exactly when it breaks, and you break it hard, and you try everything that you can figure out on a thing that the devs believe is perfect, and you will go and break it. That's your mission. And Cesar is a master at that mission. and so he has a dedicated test team, and they will find those things out. There is a lot of people are doing testing, like when I see test-driven development, and now I'm going to step onto everybody's toes. It makes me cringe a little bit. Because the outcome of test-driven development is supposed to be a well-tested system. I don't think that's true. I think that's you can prove that functionally you've done everything right. But that doesn't mean that your system is performing right. Because there's so much test that needs to happen that is different. Stress. Really testing the system under high load. Endurance. Right? Put your system under average load and let it run for 72 hours and let's see how that looks. You know, watching the trend lines as you do this. Have a memory leak? Because if you don't do an endurance test, well, how do you know that your system is not leaking memory? And if it only leaks an object here or there, you're not going to stay up forever. Right? You ought to stay up for a month. Well, the only way you can find this out is if you have ways to go and do endurance tests and actually log those things and figure them out and actually track them. There's all kinds of security, pen testing, there's all kinds of testing aspects that you don't catch if your testing model is, let's write a unit test. And then let's write the functions into that unit test. Yes, you do functional testing with that, but you don't do systems testing. You don't test the back end in that way. So it's not sufficient. So I actually tend to have a bias, and that's probably an old habit, that I'm fairly light on unit tests, but I usually do end-to-end tests. With the knowledge that I have of that code, like when I do the developer testing, I try to exercise as many of the code paths that I do as I can, try to hit it all, and I try to go for coverage. But I'm not trying to be anal to go and hit every single function kind of singly, individually, but I try to maximize coverage instead of trying to maximize function calls. So what we do is we test those configurations. And if we know that we're hitting capacity, and I'm going to get to that point, capacity, in a moment. If we know whether we're close to or hitting capacity, we can go and inflate or deflate from a point to another point. So we take an existing deployment and make that bigger, or we shrink it. But we don't have a robot that sits there, right, watching the numbers that will then happily jump off its chair and start dialing things. That doesn't happen. We have very well-known metrics that we do that with, because it's hard to automate those things. And once you kind of hit an odd untested number, it's kind of hard to do. So we call this concept scale unit. Scale unit is a well-defined unit of scale in your system where you know all the parameters. You know exactly how much capacity you have for this. And that's something that we test out. So we make a scale unit of 4 by 4, and then we stress it, and we can see how many queues and how many topics and how many relays we can sustain on that thing. And then we kind of dial it down and kind of measure it to a healthy state. So that's the 4 by 4. And we go to the 16 by 16, 30 by 32. So we measure what the capacity is. What also contributes to that is that we know what the scalability goals for the underlying resources are. So we know we have a SQL database underneath it. We have a table storage underneath it. We have resources, and all of those things are physical. Right? Ultimately, yes, it's all virtualized, blah, blah, blah. But you have a table store, and on table store, you can actually go and read the Windows storage documentation that says our scalability goals are the following. Bop, 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 bop. You have actually the same thing for Service Bus. Our scalability goals are this and this and this and this. This is what you should expect in terms of throughput. You go through the list of your dependencies, and you go through the list of what you do in your app, and you take those numbers, and they will tell you what your physical world looks like. Because it's not cyberspace, right? It's not a mythical space you can go in there and then drive a motorbike, like in Tron. And you drive into a wall, and then the wall kind of goes away. No, you're actually going to hit that wall because it's physical. These are physical things that are giving you actually hard constraints. Ultimately, what we're doing here in the data center is we're taking a general purpose machine and turning it into a special purpose thing. But it has limits. It has limited memory, it has limited throughput, it has limited network, it has limited X. So what you do is you look at you build your thing and you look at the resources that you have and you say, I have a database connection. And you look at the database and it says, well, that's rated for, and I have tested it out to X transactions per second. And I have a storage account, and the storage account can only do so many inserts on a single account. And you take those things together, and you effectively calculate out how many transactions of your system you can go and do it. It's actually deterministic. That's a nice thing about a Turing machine, that it is deterministic. There's no, in those limits, you can actually go and calculate those things. And then you actually need to give yourself a little bit of padding, right, with those numbers. So if the table storage guys say, we can do 1,000 transactions per second, then you don't use 1,000 transactions per second, but you use kind of half of it or a third of that. Because there might be bad times. And you also have to go and deal with bad times. And you also need to go and deal with outages. And if you get pressure from above and you need to do retries, well, then there's time where you are starting to have a traffic jam in your system. You need to go and deal with a traffic jam. But it's physical stuff. So you can go and calculate this out. And I actually have an article on MSDN, an MSDN magazine, in the June and July issues, which is about the Internet of Things, where I talk about scale units and also in particular kind of do a little bit of that kind of math for a sensor that sits in an air conditioner and kind of walk you through that. Ultimately, what you're going to arrive at is some capacity numbers. So you have things like users which are requesting, or you're providing an API to people. You have people, you have machines, you have things that are talking to your system. And those have a particular usage pattern. That's the other thing you need to know. Right? If we're planning, we know exactly how many queues can we sustain, how many things can we sustain, etc. We also know our users, usage tracking. So we know, well, for calculation, if you're making a namespace, you're going to consume the following resources. The way we defend against you not doing more of that, actually breaking our calculation, is first is math, so statistics. The second is quotas. So if you come into the system and you start, oh, now I'm going to make 1 million queues, well, you can't because there's a quota in place. The quota is a hard, sometimes a dialable limit that's in the system that we apply, that if you come in and you want to make the queue number 10,001, you can't, because we've counted them all. We're good at arithmetic, at least with adding and subtracting. So we won't let you do that. We will actually let you do that, but then you have to pick up your phone and say, Microsoft, I want to make 400,000 queues. And we'll say, that is fairly crazy. Let me talk to you about that. Because you probably want to have topics and 400,000 subscriptions, and with that, I can certainly help you. So you put some quotas in where you kind of allow the Wild West to sprawl and happen. And then once people get really serious about your resource consumption, you say, oh, there's a quota. You could have more, but you come talk to me. And we're going to talk about your architecture. And so that's one of the measures that we have in the system. Okay.
After which percent after which threshold do you basically scale up on your units?
See? We don't let that happen. So,
I mean, after which percent do you move to the next one? So 33 or 32 scale units?
So as I said, as I just started with, let me answer. I'll answer your question as I keep talking. This talk is going well. I hope the recording turns out okay. So far, I also haven't talked about any secrets that will get me fired. So that's a good thing.
And also, you have to tell us where the service bus relay sits. Is it gateway or is it?
It's in the gateway because it's a purely it's just a forward. It's just a networking service. So the relay actually sits over there, right? Capacity. The provisioning service. Here we go again, right? The provisioning service is part of that story. Every scale unit, since it's all tested out, has a known capacity. Every user has a known allocation, and then with some math and playing the lottery, we kind of can guess how many resources one of those namespaces will consume. Same for you. Right? If you're running a multi-user system or a multi-tenant system, you can do first a guess, and then second, if you do usage tracking, you actually have data that will support that. Where you can say a user will come in, so a bunch of users will come in and never use any resources. Other users will be super heavy users, but the average user is going to look like this. So as you are creating a namespace, you have a maximum you have a maximum quota if you create a tenant. And then as you learn about the system, you can actually be looser on quotas. Like think about Outlook.com or Gmail, right? No quota. Because they have learned so far, they have learned so much about their capacity allocation that they know how they can go and efficiently manage that without having a hard quota in place. But they have quotas, but they'll soft quotas and they'll bump you up if they need to, but they can go and move you if they need to. But if you have so you might have hard quotas in place in your system, and then with the quotas are defense, and otherwise you use statistics to kind of guess how much capacity you need. And then you stand up those scale units. So you start when you have a data center, and the data center sits in a region of the world where you don't have as many customers. You start with a small one because you want to save money, and the small one has a capacity of 100 customers. You go and you deploy, and you add customers to that scale unit. You have two choices: either customer 101 comes, you make that thing bigger, or you stand up a new scale unit and let that other customer go into that system. That depends on how separate the pillars are that you have. If you have a system which is really focused on personal information, for instance, and it's very easy to partition and shard, having a model where you have those systems kind of stand up side by side is actually a better one. Tie that back to Gmail was down, right? Or Hotmail is down, or there's a website that's called, I think, isitjustme.com or something like that, right? And mostly with well-designed systems, the answer you're going to get is, yep, it's just you. Because it's unlikely that your other 5,000 friends are sitting on the same scale unit as you are. Another nice aspect of those scale units is that you have a focused set of resources that are exclusive to that scale unit. So underneath this sits table store accounts, which sit in certain clusters. There's SQL servers, which also sit in certain clusters, so they're also operating the scale units. And if one of those scale units dies, because let's say there was a master database, and you can't survive without that master database with your caches. Might be. Well, then you're going to lose that scale unit, but you're not going to use all of them. If you're splitting your system up in that way, if you're actually having scale units and you allocate your customers onto those scale units, and you take your customer population, spread it across those scale units, you can never be down. For an individual user, you can't be. But the system per se will never be down. So I can stand here and say, Service Bus has never been down. Because it never has been. Because we're running across 8 data centers. And we're running scale units in those data centers. So yes, we have had episodes for individual customers, and we actually have had episodes with individual data centers because infrastructure around us, we weren't reachable, for instance. But since we launched, we've never been down. And we've never been down because we're splitting up the system that way. So that is actually doable for a lot of the stuff that people do, also for multi-user systems and for multi-tenant systems. Let me go and give you, it's actually fairly simple how we do this. So let me talk about that, and then I'll talk about some alternatives. So let's go and stick with the gateway for a moment. How do I allocate a user to a scale unit? Well, the scale unit has a name in the system. foobar XYZ, that's the name of my service. -EU West -1, it's the name of my scale unit, so I can go and effectively say environment or application name, data center number, reasonable naming scheme, .cloudapp.net. So what I'll do is I will make first deployments across all the data centers. I go into all 8 data centers, obviously, right? And go make deployments, because the deployments that don't have anything deployed in them, don't cost you anything. So you can go and make deployments. Make them. And so then I have a name for that. Now a customer comes along and says, I want to use that. Well, then you're going to tell that user, you go to the following place. Now, going to that following place you could do in the cheap way, as we've done that, and that is use DNS. So if I make clemens.servicebus.windows.net, what that is a CNAME over the deployment here. And so if I go and resolve this, I'm going to resolve to that particular scale unit. Doing that via DNS has actually enormous advantages, and has allowed us twice to do a fairly interesting trick. Imagine this was a decked out table, and all the good china is out, right? Everything that we inherited from grandma. And there's a wonderful tablecloth, however, it has a stain in it. So what I need to do is I need to get rid of that stain, which means I take the tablecloth, pull it, leave everything on the table, right? That's already a wonderful trick. And everybody would clap if I was really doing this. But then the better trick is to take the clean tablecloth and slip that underneath all the china while that's there. Now that would be a trick that would make me a rich man, and I wouldn't have to work in information technology. An even richer man. And hello to my friends at Facebook, who actually they were lucky. So, we have done that twice. We have upgraded Service Bus with everybody's systems running, all your dependencies, while taking you and moving you from one cluster to the next cluster without any service interruption. Thanks to our DNS method. Effectively, you're sitting on, we have you with your namespace and X thousands of your closest friends are sharing a scale in Service Bus. You're hammering like crazy. We're standing up a new scale unit, and we're actually sometimes doing weeks of engineering work to do those upgrades. Because we have a promise, and the promise is we're never going to go down, at least not in a planned way. We don't go down in a planned way. So we're standing up a new scale unit, side by side, completely new deployment, because we've changed the configuration, we're adding a new network protocol, etc. It's not avoidable. We're standing that thing up, we're doing a smoke test on that thing, and now we're actually starting to bleed configuration data from here, kind of replicate configuration data from here, from the operational store in the other system. So the transactions that are happening in here are happening twice. We might do, to prepare that upgrade, we actually might do a rolling upgrade of this guy, right? So that will go and do that replication on the fly. So we might run a new version of the old code to support that upgrade process. Then we're running scripts that will take the DNS records and dial down the TTL, which is typically a few hours, so that the DNS machines don't get hammered too much. But we dial that down to stepwise to as little as 2 seconds. And the interesting thing with a global DNS system is it is good about TTL. It really is good about TTL. If you have a cache and you give a cache a record and you tell that cache that record is only good for 2 seconds, it will adhere to the 2 seconds. So now we're waiting until the clock hour has arrived, at which everybody, based on that calculation, should have now effectively hitting the DNS server for every request, every time it needs to do a name resolution. At that point in time, with everything synchronized, we do a switch over and run a script that will go and switch all these DNS records over to that new system. So we're now starting to take that data into the new system, all that traffic into the new system, until all that has happened. At that point in time, we're seeing effectively traffic die down from this one. And traffic dying down means, now this is all built to be failure resilient, right? Also, our client is built in a way that it can deal with a server going down. So effectively, as we have switched everybody over, what we do with this guy is we tear it down forcefully. We effectively make it crash, which forces everybody who has existing connections to go and re-resolve and go to the new guy. And then we just take that on, all throw it away. Done that twice. You can do that because DNS is actually a good way to go and do that switchover. That's one way. So you can do this with custom domains as well. If you give us control over your records, then we could do that with custom domains as well, because we can point them to our things. And actually, CNAMEs, so CNAMEs bolting them to an environment is one way, and that's kind of what we do with the explicit config. But having another indirection here, where we give you a logical name and then we flip that logical name over, is a way how we can go and achieve the same thing. So that was the failover upgrade story. How do you do this with a clustered system when you don't want to have this? So with Clemens Vasters Service Bus and Windows.net, obviously that kind of bleeds through. That doesn't look pretty. The way we make this work, by the way, with SSL is we use certs with a little star, wildcard certs. Sorry, it's getting late. Use the wildcard certs, which then are working for that particular name. So the other way you can do this, you can make this pretty, but still kind of remain in that clustered way, is to have another gateway sitting on top, a routing gateway. And in ASP.NET, you can use, and actually the gateway's job would that be, so either you have that kind of, you see that as a function of the gateway, or you see that as a function of another layer that sits on top of it. Let's make this a function of the gateway. You can use stuff like application request routing, ARR. Application request routing gives you effectively one face, a stateless face for your application. And you come in with a request, and the request contains a cookie, and that cookie contains your identity. Based on that identity, it routes you to a particular scale unit. It routes you to a particular place. So you can keep that gateway completely widely distributed. You simply have a cache on each machine that kind of does a map of user to the particular scale unit. Or if you're Facebook, you're probably and you have a billion customers, you probably have a little bit more sophisticated thing there. But typically, for most systems, it's enough to have a cache on machine, so you can go and replicate this out, do that mapping, and then you can have a pretty face. All the requests come in, and then you route those requests to the respective cluster, so that parts of your population may be down because the cluster is down, but you have so many gateways, and they're also in separate deployments, but they can go and cross-route between deployments if your system generally is not down. So you can do that as well. You can put a pretty face on the system by having that application request routing layer, where with the domain name, you make the clients go to the right place. And with the application request routing layer, you kind of take the traffic into a generic gateway and then route that request kind of in a two-step way down. If you think about, in a moment, if you think about, or if you look at Hotmail, for instance, if you log into Hotmail, you will see that in Hotmail, you go and you go actually to your machine. You go to your cluster where you sit. So that's actually sitting inside the address bar, sits the cluster name, or I don't think it's the machine name, but the logical cluster name where you sit. And then from there, it gets subdivided. So you actually get punted into that cluster, and then based on your identity, they're actually picking out who you are, and then they're also co-locating your resources that way. So for building larger systems, right, the clustering based on availability, on capacity, and then making those STAMs side by side that are sitting there that you can then route to either by doing direct DNS routing or by using this request routing thing. That is one of the secrets to be never down. It turns out that most of the data, and that's me conjecturing, I believe strongly that most of the data that's volatile that is changed by users is if it's focused on if it's focused on a particular user, you can make a bucket that belongs to that user, and you can go and route towards that bucket and get that changing data. If you have information which is if information that's focused on a particular person, on a particular thing, yeah, there may be volatile data, and it might matter that you have just made a change on an address, right? And so the shipping address just changed, and you need to know this the next second. So it might be okay to in a distributed system to go and route to that place if you need to know about personal data from that particular person. Most other data that's not focused on a particular bucket is roll-ups, statistics, read-only data that's being produced, events. There's some event sourcing fans here. Events information is data that is effectively once generated that never changes. Lots of data never changes, and if data never changes, it's actually fairly easy to replicate. So all the scale units can know a digest of it, or you can store it in a big warehouse and go and replicate that warehouse out, and you can make it scale big. It can make very many copies, so you can go and route people to it. Use the CDN, for instance, or use something like the CDN to it. There's only very few data which is truly volatile, where you're actually doing updates, where you say, this is the latest record, and this is the one that you ought to use. And projections, things that you're using kind of for operational. What's my current shipping address, right? What's my current configuration state? And I think it's reasonable if you have a particular device, if you have a particular person, is make it in a cluster, scale out a cluster, and then walk up to that bucket and get the data from there. You don't have to have it completely in a single database. If you need to do queries, if you're asking for a particular person and you don't know who that person is, but you only know that that person has shoe size 43 and has blue eyes, ask all the clusters, right? Do a fan out query, get the results back, and that's also reasonable. You don't need to have very few cases where you actually need to have a single consolidated database. Typically, you can do cluster things out, walk to the bucket which contains that data in network systems, and otherwise keep read-only data or data that's purely additive, insert-only databases. You can go and replicate that very, very easily and also make that scale very easily. Let me stick with that address information. It actually turns out that shipping address is one of those data items where people say, well, that's an update. Right? You have a record, it sits in a database, you have the shipping address, and the shipping address is a very obvious database update. In my previous life, well before I worked for Microsoft and then before I had my own company, I've been writing financial software, specifically financial software for the dark side of the force, for financial collections. Turns out, in financial collections, that would be considered destruction of information. Because it turns out that where you have lived, where a customer has lived, is very useful information if that customer starts not paying you in 7 years. Holding on to that data is actually very valuable, because you can go and send the collector to the previous places where you've lived, and the collector goes and rings the bells to some doors and says, do you know where Mr. Müller is? Yeah, he's been here, blah, blah, blah. And so you ask his former neighbors where he might show up, or they might know through some corners because people know people, and that's how they track them down. So actually doing updates on innocuous data sometimes is, from a business perspective, fairly stupid, because you're destroying information that you had. So adding stuff, doing inserts, keeping logs is often a really good thing. So storing data as a chronology often is a very good thing. always keep in mind when you build a business system, update destroys information. Update is a delete with an insert. So think hard whether you really want to do that, whether you want to do that delete before you do that insert. And if you do only insert systems, so if you just add data, now you have data that actually lends itself to flow through a larger system and to be replicated. And then we get to the point of eventual consistency that was raised earlier, where the question is, does all that data need to be in sync everywhere at the same time all at once? And the answer is no. Facebook, Twitter, very many other systems, you put data into the system, they don't allow you to delete it, to edit it, right? What they allow you to do is they allow you to delete it, so you can go and do effectively an undo of the record. But you put data into the system, and that data you put into the system can flow towards all the buckets that are your timeline. And that's what you subscribe to, so it can be consolidated in that place. And then if you want to delete something, well, then you send a message after it, which goes and then cancels out what you had before. In financial accounting, there's no delete. Everything has a record. If you want to go and undo a transfer of 100 euros from one account to the next account, well, you do the inverse and do a debit. Once you embrace that notion of having additive data, and if you have a system that's suitable for it, then that's a good thing. You have a lot of that in all the systems, diagnostics logs, and you have all that stuff already, which is easily replicable, which you can go and reshape in all kinds of forms. But often that also applies to business data you have in the system, not to all data. For instance, in our systems, in Service Bus in particular, if you make a queue and you delete a queue, well, you will typically want to get rid of that and you won't ask for it back, except sometimes. So we also never delete stuff. Eventually we will reclaim it, because it would be stupid to keep the baggage around. But if we do deletes, or if we do updates, we always do soft deletes and soft updates, which means we keep the old records around and mark them as invalid. Sometimes it's a flag, it's a Boolean yes or no. Sometimes it's just a valid until flag, which means this was valid just until a moment ago, but you keep a chronology around. The reason why that happens is because people are stupid. And someone very well-meaning goes around and runs a script, and that script does something that is not what they're supposed to do, or they misunderstood something. Seen it all. So we had a case, for instance, where we had some resources, namespaces, which got deleted because some promotion that they were created under, the promotion was over. And so the accounts that we're giving out in cars kind of expired, and then we wanted to go and wipe them all out. Turns out some cards got mixed up, and someone got a card and then upgraded to a particular other offer, blah, 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 blah. So stuff got deleted. It's kind of bad. I was in the room, in the emergency, oh my God, we're screwed room, as that hit, or actually I walked into that room. And but after that hit, and then we said, well, good thing we have soft delete. So we went into the operational database, flipped all the bits, and all the data was back. No data loss whatsoever because we didn't delete it. So we give ourselves a grace period where we can compensate for stupidity, but because we don't delete, we don't destroy it, we just hide it. So we hide it for a while, and then once we're sure that nobody is interested in it, then the garbage collector comes around and carts it off. So inserting is really good for scalability because you're going to go and replicate the data out. And the soft deletes are actually useful to compensate for stupid. replicating. So far you have noticed I've spoken a little bit about how we do things, even though I haven't given you too much detail about the internal, so to keep my team happy. Even though you could find some of that data if you were caring enough. I'm not going to show you, I'm not going to tell you where, but a lot of that of the internals out there. So let me talk quickly about Service Bus and how that pertains to all that stuff, because it actually matters. So we have a Service Bus has a number of uses in those kinds of environments. First of all, let's talk about the relay. The relay is typically seen as a way how you can bridge from on-premise to the cloud, and it's perfect. It's actually perfect for that. It's also giving you a nice way to go and address individual machines across network boundaries. So if you build multiple scale units and you want to go and talk to individual machines, you can actually go and host an endpoint on the relay and make your machines individually addressable. You can actually go and have a web service sitting in there, which is sitting kind of on the internal network, if you will. And instead of using the internal network, you can actually speak between the machines. For instance, for diagnostics purposes, if you want to go and just take a look at a particular node, how that feels, you can use relay for that. I would love to use that, but we can't use that internally because we're running the relay. So that's one use for the relay. So most of the other uses are interesting uses of messaging. If you take messaging, this is what kind of black is a good color. I was talking about diagnostics. We have topics in the system. Topics are pub/sub infrastructure, and you can go and use topics to go and get data into a topic. It's a scale unit principle. A topic can take about 1,500 messages per second if you're inside the data center. It can actually do more, but that's kind of what we tell you in the documentation. So across in the data center, 1,500 messages per second. That's 1,500 times 1K. That's the nominal unit. If you do some nagling, which is a smart thing, and for which I'm also going to give you some frameworky things in the not too distant future, through GitHub, or sorry, no, through Codeplex. Sorry, no laughing. Through Codeplex. If you go and do some nagling, which means you take a number of little messages and bunch them together into a big message, you actually get higher throughput through that if you count messages. I can do with little messages that I send, like little telemetry messages of like 16 bytes, which is for telemetry actually fine. I can do 30,000 messages a second, even from my house to the next data center, no problem. So message is a strange unit, and it all depends on what your payload is, but the norm payload that we have is 1K, but depending on what you do, you might have more or less. So you have a topic, and depending on what your workload looks like, what your diagnostics load looks like, you may have a topic pinned to a number of backend roles, maybe all of them, maybe a subset of them. How do you do a subset without having any computer science in it? Very simple. You say topic 1 is owned by roles 1 through 4. Every role in Windows Azure has a role instance number, and then has a suffix that is its number. You can take that number and do ownership calculations on that. So you say, role 1 to 4 owns this resource, role 5 through 8 owns this resource. So you can basically you can base ownership of resources based on the instance ID, because the instance ID is a stable thing. That instance goes down, it comes up with the same, the next one comes in with the same instance ID. So you can go and assign ownerships like this. So you have a topic, diagnostics data that you don't want to find in the logs, but that's urgent enough, important enough to see right away, you bleed off into a topic. And now you can go and have a subscription on this, which says, well, you now take some information from the log entry and say severity, module, information that you would typically have as properties in something like log4net, and you put them on the message, and now you can go in the subscription and say, I want to see in that subscription everything that has severity 1 or severity 0. We're actually using severity 1 as the most severe thing. Machine just crashed, or severity 2. And so you get now out of the pub/sub system, you can have a subscription which goes and effectively delivers you If on any machine something really of great gravity happens, you can get this into here. What you can also do, so let's say you have to partition this out. So you're figuring out that the ingress before filtering into these topics is going to be too high to fit into a single topic. So you expect more than 1,500 messages per second into that topic. So you're going to go and pair these guys. Sorry, I'm going to go and clean this up a little bit more. So you're going to, hey, all right. So you're going to pair these guys up. And we're going to do these three, these two, and these two. And so now they're going to get their own topics assigned. That guy gets one. That guy gets one. That guy gets one. So now they're pumping all their data in here, all the information that they have, and now that gets filtered down based on criteria that we have. Let's say you have this alerting, very important severity 1 filter on here. So that will only catch the subset of the messages that is severity 1. You have the same guy here, and you have the same guy here. We have a brand new feature called forward to, where you can now tell that subscription to take whatever shows up in that subscription and forward it to another place. So you make another topic, which is kind of the consolidation topic, where you go and point those guys to. And now your alerting application sits with the subscription on this guy, and that's how you pull the step 1s out of the system. So you kind of bleed them. The higher load goes in here. You can go and filter this down. You can go and log this into a store from a subscription if you wanted to. I'm actually going to give you a pump very soon that I'm building something called Service Bus Plus that you're going to hear about. That's effectively an open source library that will give you things that are interesting on the application level above the API. And so in Service Bus Plus, you're going to have a pump that effectively pulls on a subscription and writes straight to the table store. So you can go and build your log this way. But if you want to do this alerting thing, you can go and have that sitting on a subscription and then bleed that off into the consolidation topic and try to create an inverse tree like this. If you can also do trees kind of in the opposite direction, just that as a tangent. If you wanted to go and broadcast information, let's say you have super many roles. Let's invert that picture, right? The subscriptions now sit at the top. And you have cache information you want to update. So you have read-only information that you update somewhere, and all the machines need to know about it. What you do is you drop that at the bottom into a topic. That topic has a subscription for each of the topics that talks to the individual nodes. Individual nodes meaning also could be devices, right, that sit out in the field. So you may have 2,000 subscriptions can be on a topic. So if you need to have 20,000 mailboxes or 200,000 mailboxes, where you have one for each device, you can go and build that as a tree. Drop one message in, they get auto-forwarded into all those guys. And with that, you kind of get that replication of data kind of as for free as a function of Service Bus and that forward to feature. Cache replenishment is a good candidate for that. Notifications. And then with that, with the rules that you have, with the rules on those subscriptions where you can effectively filter on individual properties, you can do group casts. You could say, only the machines in the following role should do the following thing, right? Or if you're whatever criteria you come up with. So you can do group broadcast, group cast, or you can do unicast through the same thing, where a rule here, the subscription rule that this machine can have, it says my instance number is this. So I'm instance number 0 in this role, and that's one of the rules that you have on that topic on the subscription. Say if role equals my name, and so you can go and send in with the property set role equals my name. That will flood through the topic through that whole tree, but it will not hit the filters in any places except that one. So with that, you're sending more data than you need to, obviously, but you're hitting that one. So if you are typically doing broadcast or groupcast, and sometimes need to do unicast, that's actually a very reasonable model to go. Another thing you can do, also with that same kind of infrastructure, is you can send packages of data. If you need to go and offload effectively from a machine something that's a little bigger, or sometimes bigger, data than the 256K that we constrain you to for messages that go through Service Bus, you can use sessions. From a send perspective, a session is effectively just labeling a session with the same ID, a message with the same ID. So for instance, if you wanted to have a diagnostic system which is keeping all the data together based on causality ID, you could do that. So let's say you have work that's spread across a cluster which is coming from a particular cause here. So you're doing some work, and now you're taking an operation that gets shred across the cluster. It has one cause, one operation that you're executing, and that happens across the cluster. And now we want to have effectively error information relating to that task, which comes from all kinds of different places. What you can do is you can set the session ID on that message as it comes in and gets sent through your system. On the subscription level, you can now enable session support. What that will do is all the receivers that are sitting behind a subscription or queue with session support will now be pinned to that session. So you can say, as you say with socket, accept socket, you can say accept message session. And you can either give an ID or you do it anonymously. And now, if you accept session, if you get that session, all the messages with that same session ID get routed to that one receiver. Which means with that we give you demultiplexing of multiplex streams. So you can come in with all that data that gets filtered in here. You get that data routed, kind of concentrated by severity ID, severity 1, to that one topic. And now you're interested particularly in that one transaction that goes wrong, right? So if you prepared for this, well, then you can go and effectively you can go and do an anonymous accept of that session, and pull all the data that came in for that particular cause, and pull that out and write that in sequence into a log and have that all nicely together. Because the session feature bundles that on the same machine, but even better, you have a longer running thing. Something that takes something like 20 minutes. God, I wish I would be able to talk about this. Oop, please. There's a game that's using that. The game's actually pretty cool. So, did I make a mess of myself? Yes. So let's say you have work that's going on for about 20 minutes or so, right? And you want to go and collect results like this, or collect diagnostics data, etc. You want to collect stuff like that. So you're flowing information, status information, doesn't need to be diagnostics information, but status information about a particular job. And you want to do that kind of demultiplexing. So it shows up at a particular subscription. That subscription is session enabled. Maybe you know about that job. So you're creating a job because you're in control, right? It comes from above, and you say, this is my job ID. Session IDs are free form, so it's all good. On that machine, where you sent that job, you also have a subscription, and now since we can edit rules, right, you say, session ID, right, that session ID, I now want to go and wait for. So you go and have the session, you do the routing, you say, if the session ID equals so-and-so, I want to have that message, I want to have those messages. And now you say accept message session with that ID. You just wait for the messages to show up. Or you do that anonymously, depending on how you want it. But let's say we wait for a particular one. Wait for the particular one. The data comes in, and what you get is effectively a scatter-gather, where you scatter the data out, and now you're just waiting here, waiting for your demultiplex stream on that subscription, which sits on the server, and you're gathering the data into your session. You can also do this in a failover way. So let's say you're writing the data specifically into a log. Your job is to go and assemble that data into a log. Into a log that's together, that belongs to a single thing. Let's say you're writing a multiplayer game. And in a multiplayer game, there's a long game that's going on, and you want to collect all the statistics that happen in that game, in the multiplayer session. Well, then you could go and sit there with a generic listener on that subscription, say accept message session. You get a session, you get a message, and now you want to write that into your data store, right? This is the current status of how that session looks. But you want to be stateless, you don't want to know. Where do you store how many messages I've seen? Is that the first message, the last message? Where am I relative to those things? Do I have to go to the data store? How do I scale the data store? Well, for that we have a wonderful feature called session state. So our Service Bus sessions not only allow you to do multiplex, but they also allow you to put a cookie into the system. So you can get a message, say accept a session anonymously. You say accept message session like you accept a socket. And then you say get state on that session, say, do I have remembered anything? No. Okay, let's take this message and let's go and play this on my code, on my logic. That will morph my state from initial to the next state. Let's go and take that state and store it. Set state in that session. Next message comes along. You take the previous state, play the data on that state, and save it again. You don't save it to the database because it's still ephemeral, right? We're not done with that operation yet. The operation is going on. And then once you are done, all the messages, all the 10 messages you were waiting for have arrived. Then you can go and store that data into the state because then your state machine is done working. So it turns out this get state, set state that we have on sessions is actually made for state machines. Turns out it's made so well for state machines that the workflow in SharePoint Office 365 and SharePoint 2013 is based on that feature. So it's a state engine support infrastructure so that your state machine can actually be fully stateful and that state gets stored in where the messages came from. Now, so now you're going to say, hey, wait, so how do I deal with the situation that I wait for 10 messages, but I only get 9? And then the 10 never arrived. How do I get to that point? Very simple trick. We have a feature called scheduled messages. As the first message comes in, and you are showing up with a null state in the session, you send yourself a scheduled message for in 20 minutes. And that's the termination message. That's where the session is going to end, because that's kind of your timeout. And then you collect the other messages. And if a message doesn't show up, well, then you're going to go and you're going to get the termination message after 20 minutes because the system is going to send that to you. And you can terminate. At that point, you can either choose to leave a trace in that session, kind of leave a non-null state in that session, minimal. That actually counts towards your storage quota, but it might be very tiny. To defend against further use, and then send you a further scheduled message, in 2 days that will then actually go and reclaim the garbage, so that shows up again. So we have a state engine in there which allows you to go and actually deal with more sophisticated message flow patterns that may come out of stuff that happens in your system. So Service Bus is a very useful tool for all kinds of those operational below the waterline iceberg effects that you have in usage tracking, because it allows you to go and flow data into an intermediate layer, which you might have, which is going to do roll-ups, and then push things further. You might want to take a look at Stream Insight. Stream Insight is a wonderful system to go and aggregate information, and then send that further. And it's a great system to also think about diagnostics and flowing the diagnostics information out of your system. In addition to being a fairly well-suited thing to do that kind of communication. The latencies that we have in Service Bus on the server side, on the service side, in the service, in the deployed service, right now are on if you go through a queue, so if you send messages through a queue, are about in the order of 20 to 30, and on the battery 40 milliseconds. So if you have heavy load if you have unpredictable load on the back end, if you actually need to have additional kind of defense here, so if you have a system which has huge spikes during the day, and that workload here on the back is somewhat expensive, right? You need to do 3-4 database operations to do a single thing. Then it might be worth not doing this as a one-way, as a request response path, but actually putting that data into a queue. Because if push comes to shove and you actually get stress from the front, you don't get stress on the back because you're pulling the data out. You're not getting it pushed to you. The round trip latency here is for heavy workloads only tolerable, right? If we're talking about that flow rate, we're talking about 60, 70 milliseconds as a round trip latency if you go through a queue from a queue. And that's all transactional. So all the messages are always persistent to disk in our system. One piece of work that we're doing that in conjunction and in cooperation with the SignalR team in ASP.NET, is we're introducing a notion of volatile entities. So that's going to reduce down effectively you're going to trade latency for reliability, because the time goes somewhere, and actually the time actually goes in the trip to disk and back. So we're going to cut that out, which means we then might lose messages which might not interest you here all that much, right? Because you need to have that buffering. So you can effectively we're going to allow you to trade reliability for latency with that model. But it's very well worth taking a look at this model. We have, again, sessions are a great way to do that kind of correlation, because you can sit here and wait for a particular session, particular response, and to do the demultiplexing that way. You sit on a shared resource across multiple nodes, across multiple threads, and you can ask for particular messages back effectively in a particular session. You send a message in, say, this is my session ID. You wait there, you say, accept message session. For that, you're waiting for that particular session ID. As that arrives, you get that back. And so that gets marshaled, if you will, on your waiting thread that sits here, waiting thread, logical thread, because, of course, you all are going to do that async and use begin accept message session with that parameter, because that's a good idea. The other way of doing this is by having a shared listener sitting on the reply queue and pass that reply queue along as you do that request. So there's a number of different patterns, and since that's a lot of details of how to do all those things, those are kind of hard to remember and they're hard to touch and understand without samples, something is going to happen as I'm drawing to a close. I'm very happy that so far I haven't seen anybody leave yet, but that's probably because I didn't pay attention, but probably because nobody left yet. There is an application that's kind of sitting on, I think it's sitting on that machine, that's waiting for a release. It's not a true app. It's kind of a half app. It's a not so serious app. The company is called MartView. MartView is a loyalty CRM marketing SaaS agency, and they're helping retail companies realize their full potential. All the Microsoft people in the room should now be proud of it. What it does is that company sits on the wire from the point of sale of retail companies to their headquarters, taking data that flows and managing loyalty systems. And loyalty systems, let me see whether I have a loyalty system thing here. I do, today I don't have that with, yeah, I do. So this is the Düsseldorf airport card, right? That card exactly gives me very little, except on weekends, cheaper parking for 3 hours, and it also gets me into the observation deck cheaper. That's what I care about. It also gives me discounts at retailers. What I trade for that card is my privacy, because as I got that card, I had to give them my address. so they can give me customized, wonderful marketing, right? That's the trade that you do. So that is what MartView does. MartView is tracking these loyalty things, and they're giving you customized information. What they do is they do even more. They are specializing on supermarkets, and therefore they're taking, every time you swipe the card, they take your entire receipt. And then they put that receipt into a huge data store that's sharded. It's your bucket. You can get to your bucket. And then that data gets dissected, flows out. You can get custom reports on what you spend on butter throughout the year, right? All those wonderful things. That is the scenario that is MartView. That has been created entirely, with some exceptions, in my head. So it's not a customer scenario, but it is not completely dreamt up, because we have customers who are doing things that are very similar like this. And I actually keep hearing about customers who, oh, I have this wonderful lead from the Microsoft field, and it turns out they're doing exactly what MartView does. So it's not that far away. The goal of the MartView application is not to build that CRM app. It's actually to have a tangible scenario that you can all relate to, because most of you have a card like that in your pocket somewhere. And most of you have grand worries, so I'm confirming all of them with that scenario. And then take slices out of that scenario and actually make them happen. So the goal of that scenario of MartView is that I can go and take this piece and implement it. This piece, the back end of that, the database of that is going to be mocked. There's going to be one page, and you can click a button, and that's the functionality of the UI. Because I'm not there to do guidance applications on ASP.NET. I'm also not there to do guidance application on Entity Framework. Mostly also because my personal ORM is called SQL Command. But that's because I'm an old man, and I've learned SQL. And so, yeah, I learned SQL. What's so funny about that? So it's not the goal to do the grand, everything Microsoft.NET guidance application, but actually do a focused thing. The problem as you're seeing with middleware is I had to talk a whole evening to kind of get to the point where you're all like, God, that's an awesome pitch. I want Service Bus now, right? Because I have to kind of set this up, and I'll put you into this big pain of, oh my God, big distributed systems are kind of hard. And here's the savior with some infrastructure, some middleware. So middleware comes into the picture once you build more sophisticated systems. So we need to build a mock kind of halfway sophisticated system to actually go present those things in context. So MartView is an application where you have to imagine about 80%, and we're going to write about 20%. So I have 4 modules. One is the introduction, which is here's how this works, and then there's 3 modules ready that are working in the following way. There's an MVC. Basically, the baseline is an MVC ASP.NET application with also services that are host. And then in the package come 3 NuGet packages. They're not public NuGet packages. There's actually a local NuGet feed. And you can go and take that code and add that to the baseline. So you can add all 3, or you can add only 2 of them, or just 1, and then go and focus on that one. And those implement one end-to-end scenario. Every scenario of that app comes with a 3,000 word document, so about MSDN magazine format, and comes with a guidance video, which I haven't shot yet, but I will. Documents are all there, and so that's going to be released step by step likely on my blog, on my new video blog. That's where those things will show up first. So MartView is the guidance application, and part of the guidance application is a shared assembly of shared utilities, and that is what Service Bus Plus is. So the goal is that you never have to write that pump again, because there's one pump, and that pump you can go and stick a callback in, and you can say, you can have some knobs, and I'm going to call you with a thing I expect that you return me a task, right? So it's async, must be async. It's ASP.NET and .NET Framework 4.5 only. Apologize. But it's made to be async, but it's also made to be easy. So that's the goal of the guidance package, so that we do things the right way, because we see people and customers do all kinds of interesting things. So we like to push that in the right direction and also give you code that you can use and also customize for your purposes. So the goal is that we're actually going to put this on Coplex and take submissions as well. So the goal is that that's an open effort and obviously free. So, yes, question?
Finally.
Huh?
Finally. So, anyway.
Finally what?
Finally, you get a question.
Yes, that's right. Finally from a completely different person. Yeah. I'm happy that someone is talking here. In Belgium, you are very, very quiet.
I'm not Belgian.
You're Greek, right?
Mediterranean countries.
Are you Greek?
Yeah.
That's okay. I didn't mean it. As I started that sentence, I didn't mean it that way. As I ended the sentence, I did. Yes.
So, one thing you didn't cover was how you recover from faults. So, if a whole scale unit goes down in instances, how do you treat that? You wait just for the fabric controller to resume, you lose the customer, you just don't care until it comes back?
Well. If that happens, yes. How do I know? I think that's the big question, right? So if that scale unit goes down, right, we have to recover from it. Recovering means often we reboot it. Just plain and simple. If it worked the last time I booted it, there's a great degree, and all the dependencies are up. There's a good chance that it will be up when I reboot it the next time, right? Because it's kind of hard to break a software system like that. So yes, rebooting is one thing. But one of the interesting, I think the more interesting point that I didn't touch on yet was how do we know?
Yeah.
So we have a suite of tests that are also owned by the test team. Another good reason to have a test team, which plays user. So we have a whole suite. It's a huge suite of tests which are just mimicking normal use, and we keep running them. So there's a dedicated place in the system, separate deployments, which do nothing but go and exercise the system. They don't put stress on it, but they do functional tests at a leisurely pace, so they don't use a lot of capacity. These are canaries. If they keel over, they raise alerts, and that's where the whole Windows Azure Lifesite team springs into action and says, Clemens, your stuff is down. And that's what happens. And we get that call. I just came off the servicing loop, as we call that thing, yesterday night. And these are weeks. We're doing that for a week. Nights of terror. Because you can be woken up at a moment's notice. So effectively there's this SLA for how quick we ought to react as a company. And if you have your ass on the line, for that, you better have your phone right next to your bed, etc. And you obsessively check your email before you go to bed, and just as you wake up. So you plan your sleep when you're on that servicing loop. So I got off that yesterday, and that's the moment where you start drinking. Like, clock strikes the hour. Thank you very much. Nothing happens. That's the good thing. But how the alerts get raised through two mechanisms. So first of all is all these test runners. Test runners run against the system and execute normal operations as they would, and they have some variation going across multiple resources. So they hit all the. We try to aspire to hit all the resources that we have in the system. We're not perfect at that yet because we have a lot of resources. Then the second thing is we employ a external system for external connectivity that is not explicitly not Microsoft. So we have an external. I don't want to do advertising. So there's a number of external availability services where you can effectively upload scripts, and they will go and shred that through their infrastructure, and are going to test whether they have connectivity to your system from their locations. So if there are networking issues on routes from one place to us, and we'll know about that through those kinds of runners. So we have external verification, and then we have internal verification on all the functionality aspects of the system, and if we see anything go wrong, the alarm bells go off, and we will typically spot things as they happen, and before you notice that. And then you spring into action, and then it all depends on what you do. Really depends on what happens.
And what happens to the namespace that belongs to that scale unit?
That depends on whether the scale. If the scale unit is down, they're down.
So
we would have to. We can move them because they're sitting on effectively sitting on a database. So let's say something went haywire in the networking. So something gets deployed in networking, and we have to declare bankruptcy on the network, on that cluster, because of networking. Because the data sits somewhere else, we can stand up that scale unit in another cluster and keep running that. Which means, and that's something that because of the CNAME, we actually have another interaction with the CNAME. So that's actually something that we can go and do fairly easily. If storage goes down, well then that's bad luck for the respective namespaces, right? If we are separated from storage, that's a tough cookie. And we have done for some of the parts, some of the aspects of storage, we will keep running. So, for instance, if we can't log usage, if we can't log billing, we will not go down. If we can't log, we will always be able to log locally. So if we can't log locally, the event log policy, right, we're going to go down. That rarely ever happens. If we can't log centrally, we'll not go down. If our central policy store, where you have your queues and your topic and where that sits, where the central in the sense of scale unit central, and central also in a limited way, but that's where your stuff sits. That's where we know that you have a queue. If that goes away, we have caching that is actually clever enough to deal with outages for a while. Where you can actually keep creating things and making things, and our caching is clever enough to deal with all that without the database. So we have resiliency in the system against outages of dependencies, and that's something that as you're running stuff, you're learning it. And so let me close with that comment, because I'm kind of starting to lose my voice and also have a 2-hour ride home. If you're building things that are larger, you have to learn how to run them. And the only way how to learn how to run them is to run them. So your stuff will fail and won't be perfect. It's okay. It's the bigger if you have something that's big, it takes on a life on its own. And you have to learn how that thing behaves. It's a monster you're kind of creating, and it has corners where it's pretty, and it has corners where it's not pretty. And you'll find those corners out, but you have to run it. And so you can't get it perfect the first time, but you need to go and plan for. Don't be stupid. So don't go in this and say naively, yes, I have tested it on 4 computers, therefore it's going to run on 40, because it won't. But otherwise, like in all the details and how much do I need to log, you got to learn your thing. And so you got to give it time, and you got to give it some also time in production, right? Yes, your users might be inconvenienced at first. If things don't go well, that's okay. But don't inconvenience them too much, right? If you know that your thing is that the ground you're on is shaky, don't throw it in their face, right? Be nice, be courteous, right? Retry if stuff doesn't work, because that's your job, and don't give up on the first try. So try to be the lookout for your users, but you'll have to go and find those things out. Every system is different, so you have to find those things out in production, and then refine it. And I can't say we're done refining ours, certainly not. So we're finding kind of technical debt in the system. So I would think that about 30% of the time that we spend in our team is all working on technical debt and dealing with those things.
Last thing, I promise.
Yes.
When are we going to see workflows back as it was in beta?
What were we
When are we going to see workflows back as it was in beta?
Workflow back as it was in beta.
22 years.
Yes. I don't think that's too far out. So SharePoint 2013 or Office 365 has workflow. That's the first indication. Second indication is there is a workflow server that we shipped alongside Service Bus 1.0 that is used by SharePoint. So if there's a workflow thing you can install on server that supports SharePoint, SharePoint in the cloud kind of has workflow. If you're clever to add one and one together, there's got to be a deployed version of that thing somewhere. We don't make that available just yet. But there's a good chance that we will make that available.
There are other things deployed as well, that they're not there, because we know currently.
Yes, there are quite a few things that are deployed.
It's the curse of the AVPs knowing that, and so that doesn't really answer, but yeah.
It's a big company. We have all kinds of things that you don't know about. Because we never said that we're not eating. So I don't think it's unreasonable to expect that you're going to see something like a workflow service sometime in the foreseeable future. How that shows up, it's not clear yet. It might be a dedicated thing. Might be a shared tenancy thing. The problem with that is it's not so easy as with Service Bus or other things, because ultimately workflow is compute, right? You're running code, and so running that as a shared option is not as obviously clearly a thing. BizTalk is the same problem, right? So BizTalk services, BizTalk as PaaS. That's also not an easy decision whether you want to make that a shared multi-tenant service or whether to make that dedicated service, because running maps, right, doing transformations is compute. And once you go into compute, you actually typically fall into the camp of doing dedicated work, or at least having dedicated options. So it's not as easy to say, we're going to do that as a service, and it's clear cut that it's going to be available and when it's going to be available. So there's work to be done. So the fact that it's available, that it's working for SharePoint, that doesn't necessarily mean that it's going to be, workflow.windows.net as a multi-tenant service. We're working through that. We have bits, and there's work to be done to figure out what the right way is to go and ship that to you. What you can do today is you can go and take the workflow service that we shipped, and or you can already use that Fabric, right, and run that in IaaS. That's what we got.